Okay. Good evening. Can you hear me? Good evening. Good evening. Yeah. So let's get started. Yesterday, we have seen problems using NMOS transistor, trying to find the operating current and voltage and the region of operation. Today, we will see one or two PMOS questions also. And you all know the analysis for NPN and PNP both are same. So similarly, the analysis for an NMOS and a PMOS, you will realize that they are also similar, right? Moreover, after that, I think in BJT, we have also seen wherein if two diodes are tied at a common point, and if both diodes are given same voltage, then we have seen that the I naught was getting distributed into two equal parts. Am I right? But if the diode potential difference is unequal, then the diode that experiences more potential difference was switching on, right? So similarly, the same thing we will see here also. Fine. Find ID1 and ID2. Now let us assume that both transistors are similar, right? Both transistors are similar. They have the same W by L, right? So the student says that Transistor is voltage controlled, but on Google it is current controlled. What should I do? Right? So now he wants me to compete with Google now. Okay. So I said that transistor is voltage controlled before biasing, right? Inherently, IC is IS into e power VB by VT. But after biasing, when you inject a current IB, it becomes a current control device, right? So transistor can be modeled as voltage controlled as well as current controlled, right? Both. But inherently it is a transconductance device, right? ID is dependent on VB, but after biasing, because IC equal to beta IB, you can say that it is current control, right? So the answer is before biasing, it is VCVS, right? After biasing, it is CCCS. Okay. Now, what if this end is -3 and this end is connected to ground? Now, what happens to ID1 and ID2? Now, suppose I say W by L1 is 2 times of W by L2. Find ID1 and ID2. W by L1 is 2 times of W by L2. Okay. I think tomorrow also we have our class, right? Because it was discontinued on a couple of occasions, 1 or 2 occasions, because of the internet problem. To compensate for that, we will take tomorrow also, on Saturday also, right? But what I requested is we'll not have more than 2 sessions, right? It's like on a Sunday, if it's like from 2 to 9 o'clock, 3 sessions, it's getting, so anytime we do, we are doing 2 sessions, right? Fine. Okay, so let's get started. So this 3 milliampere has to split into two equal parts because this end is ground. The emitter or the source terminal is connected to -10. So when it is connected to -10, definitely your VGS is going to be positive, right? Your VGS is going to be positive. 0 minus of -10. So there's almost a 10 volt difference between the ground node and the negative supply. Here, there's 10 volt there. So VGS is positive. Both experience the same potential difference. Suppose this is VS. What is the VGS of M1? 0 minus VS. VGS of M2 is 0 minus VS. Both M1 and M2 experience same potential difference. So that is the reason this current has to split into two equal parts. So we know that the source current and the drain current both are same. This is ID1 and ID2. So KCL, you can apply KCL, right? ID1 plus ID2 equal to 3 milliampere. ID1 plus ID2 equal to 3 milliampere. But ID1 is same as ID2. ID1 is same as ID2. So therefore, your ID1 equal to ID2 equal to 1.5 milliampere. Your ID1 equal to ID2 equal to 1.5 milliampere, right? Okay. Now, what about here? Suppose you take this node as a VS. M1 has a VGS of 3 minus VS. This VGS1 has 3 minus VS, whereas M2 has a VGS2. So who is VGS1 is going to be 3 minus VS, and VGS2 is going to be 0 minus VS. So from here, who is greater than whom? VGS1 is greater than VGS2. So therefore, M1 is on and M2 is off. M1 is on and M2 is off. Then what happens? All this current is steered through M1 transistor. So therefore, ID1 equal to 2 milliampere and ID2 is going to be 0 milliampere, right? ID1 is going to be 2 milliampere and ID2 is going to be 0 milliampere, right? So all this current is going to steer through Q1 transistor. I think in the gate problem, this was not ground. This was something like, if I remember, he gave minus in a gate problem. This node was, I think, minus 15 or something like that, minus 15 volt. The problem is I don't remember the values. If it's minus 15, minus of minus 10, so this is naturally negative, right? So out of these two, who experiences more is M1. So naturally M1 is going to get on, right? We'll make it minus 13. So minus 30 minus of minus 10. So this is 0 minus of minus 10. So now tell me, out of M1 and M2, who is going to get on, right? This time, M2 is VGS2 is going to be, this is VS. 0 minus VS. VGS1 is going to be minus 13 minus of VS, right? So who is less value and who is more value? So naturally VGS2 is greater than VGS1. VGS2 is greater than VGS1. So what happens now? M1, sorry, VGS2, who's 2 here? Yeah, this guy. So all this current is going to steer through. So ID2 is ID1, ID2. Let me change the color of my pen. So ID2 is going to be 2 milliampere and ID1 is 0. Now what happens if the W by L are different? What happens if the W by L are different? Tell me, what is ID1? ID1 is mu Cox W by L1 into VGS1 minus VT whole square by 2. Am I right? What is ID2? It is mu Cox W by L VGS2 minus VT whole square by 2. Remember the analogy that I've given you, F equal to ma, right? Force, mass, acceleration. Similarly here, the relationship is between current W by L and VGS. If both transistors ID are same, because the transistors are in series, then the relationship is between W by L1 and VGS, W by L and VGS, because the currents are same. But here the voltages are same. If you can see, this node is Vs. So what is VGS1? VGS1 is VG minus Vs. It is 0 minus Vs. What is VGS2? It is also 0 minus Vs. So both the gate terminals are same, VG is same, VG is same. So now in these two equations, equation 1 and 2, VGS1 is same as VGS2. VGS1 is same as VGS2. And of course mu, they're all same, Cox is same, but W by L is different. So what happens if I, oh my God, what is this pen? Equation 1 by equation 2. Then I get ID1 by ID2 equal to, cancel mu, cancel Cox, 2, VGS, everything. So you will get W by L1 by W by L2. W by L1 by W by L2. What is W by L1 by W by L2? That is 2, right? And by Kirchhoff's law, what is ID1 plus ID2? But ID1 plus ID2 equal to 2 milliampere. So solve 3 and 4, right? What is equation 3? It says that ID1 by ID2 equal to W by L1 by W by L2. What is W by L1 by W by L2? That is 2. 2, or ID1 minus 2 times of ID2 equal to 0. Am I right? But ID1 plus ID2 equal to 2 milliampere from equation 4, right? Equation 4. So what is ID1 and ID2? Today I taught my son about solving the two simultaneous equations, right? So, okay. So what is ID1 and ID2? Tell me. What's the value of ID1 and ID2? How much is ID1 and how much is ID2? ID1 is 2 ID2, but ID1 plus ID2 is 2. Why so many answers you are getting? Surprisingly, so many answers. Huh? So how much is ID1? If you multiply the equation 4 by 2, what do you get? 3 ID1 is going to be 4. 4 by 3, is it not? ID1 is 4 by 3 or 1.33. And what is ID2? ID1 plus ID2 is 2, so ID2 should be 0.66. Am I right? Okay. Now, please make a note here that if W by L1 equal to W by L2, W by L1 equal to W by L2, then your ID1 would have been equal to ID2, equal to how much? The total is 2 milli, so it would have been 1 milliampere. Okay. So if ID1 is same as ID2, then you would have had same current getting distributed into two equal parts, right? Okay. So let me repeat here. This is a foundation when we go and do current mirror circuits. Because in current mirror, the MOSFETs will be in parallel. The MOSFETs mostly will be in parallel. When they are in parallel, their VGS are going to be same. When VGS is going to be same, mostly all the current mirrors, right? If at all you want to solve gate problems on current mirrors, they are going to follow this equation. They are going to follow this equation, right? So it's very important. ID1 by ID2 is W by L1 by W by L2. So this, you're going to apply this only when VGS is same, right? Otherwise, if both transistors are in series, then what you will do? If both transistors are in series, when you do equation 1 by equation 2, in series currents are same. So ID1 and ID2 both are same. So ID1 by ID2 is going to be 1. Are you getting? So 1 is equal to W by L1 by W by L2 into VGS1 minus VT by VGS2 minus VT whole square. Are you getting? So when you do equation 1 by equation 2, when MOSFETs are in series, the currents are going to get same, so they cancel. But here, what is cancelled here? VGS1 and VGS2, because both experience the same potential difference. So this is a foundation when we do current mirror circuits, right? Okay. Yeah, I forgot. I was telling you about the PMOS, right? PMOS. So if at all you want to solve PMOS, how do you draw a PNP transistor? Unlike the NPN, the PNP has an arrow up, am I right? And what is the NPN diagram we have done? The same thing we'll repeat. What is the NPN diagram we've already done? Do you remember yesterday? The NPN one. The same diagram we shall repeat now. Yeah, I think we took some current here. Yesterday's problem, right? We took some voltage, some current. Given mu Cox W by L is how much we took yesterday? 1 milliampere per volt square, right? Find V1. Find V1. Find V1, right? And what is the other problem we have done yesterday? We took two MOSFETs in series. I didn't give you VT here, VT or mod VT. You can take 2 volt. Okay. Now let's repeat the same NMOS equation for PMOS also. And I told you what is the difference. Wherever VGS is there, you have to write VSG. Wherever VGS is there, you have to write VSG. Right? This is source. This is gate. Am I right? Wherever VT is there, you have to write mod VT. Wherever VDS is there, you have to write mod. Wherever VDS is there, you have to write VSD. Right? So what are the changes we are going to make in the equation? This is NMOS and PMOS. All right. In PMOS, VGS is replaced here with VSG. VDS is replaced with VSD. And VT is replaced with mod VT. All right. So tell me ID equal to mu Cox W by L, VGS minus VT. In the place of VGS, what should I write? VSG minus mod VT whole square by 2. Whole square by 2, right? So now it's time for substitution. ID is 2 milliampere. Mu Cox W by L is 1 milli. What is VSG? VSG equal to Vs minus Vg. Now the Vs is at V1 and Vg is at 0. So it is V1. It is V1 minus Vt, mod Vt is 2 whole square by 2. Now what is V1 here? What is V1? What is V1? Okay, so 2 2s is 4. Root 4 is 2, 2 plus. Is it 4? V1 is 4 volt, right? Now between 0 and 10, can I get 4 volt? Yeah, between 0 and 10, you can definitely get 4 volt. Am I right? Between 0 and 10, you can get 4 volt. Most of you have got 4 volt. Now the same thing here. So what is ID? ID equal to mu C ox W by L VSG minus mod Vt whole square by 2, right? So give me a substitution. There are 2 VSGs here. This is VSG1 and this is VSG2, right? So what is VSG1 and VSG2? VSG1 is VS1 minus VG1, am I right? So this is VS1, this is VG1. So VG1, so it's going to be 10 minus V1. What is VSG2? VS2 minus VG2. Your VS2, VG2. VS2 is at V1 and VG2 is at V2. And what is ID? Your ID directly is 2 milliampere. 2 milliampere. So now substitute here. Therefore, 2 milliampere equal to mu C ox W by L into VSG1. What is VSG1? 10 minus V1 minus Vt whole square by 2. Now just tell me, this is which transistor is this? M1. It is M1, right? But we know that ID1 is same as ID2. So we will have one more here, 1 milli into, for M2. For M2, what is VSG2? It is V1 minus V2 minus 2 whole square by 2. So this is the equation, right? So let me point out here, this is M2. And we know that ID1 is same as ID2 because they are in series. So this is the equation. If you solve it, you get ID V1 and V2. So let me check what is V1 and V2. Common section 2 and 6. They're saying 2 and 6. So as you go up, the voltages should be in increasing order. They say V2 is 2 and V1 is 6. What is the difference between 2 and 6? That is 4. And 10 and 6 is also 4. Very good. So there is a possibility, right? I've not checked, but 2 and 6 seems to be correct because the difference from V2 to V1 should be the same difference from V1 to 10, right? Because both the VGS are same. Okay, so I'll go with that. The answer is V1 and V2. So what is the answer? You have solved it. Let me check. If 2-3 students give the same answer, then I will confirm it. Very good. Most of you have said V1 is 6 and V2 is 2. So I'll go with that. V1 is 6 volt and V2 is 2 volt. So this is the solution. Very good. So please don't forget the formula. ID is mu C ox W by L VSG minus mod Vt whole square by 2, right? Now in series, the drain currents are same, but if you want different VSG values, suppose this VSG and this VSG want to be different, then yesterday we have done a problem where the W by L ratios are different. Please remember, in series, irrespective of W by L, Kirchhoff says that in series currents are same. Are you getting? But if currents are same, W by L is same, naturally VGS will also be same. Here, what is VGS? 10 minus 6 is 4 and 6 minus 2 is also 4, 4, 4. Why is it both VGS same, though they are in series? Because the W by L is same. Suppose if you take for the same problem, different W by L ratio, W by L1 is 2 times of W by L2 like that, then definitely your IDs will be same, but your VSG will not be same. That is why there is nothing to do in a problem where the W by Ls are same, because currents will be same, voltages will be same. Are you getting? In parallel, what is same? Voltages are same. But if voltages are same, current will also be same because the W by L is same. Are you getting? So that is why something we will do if there is a different W by L. There is no W by L change. There is nothing to do in MOSFET problem. So we'll take different W by L and see. Given W by L N equal to 2.5 W by LP. W by L N equal to 2.5 W by LP and mod VT equal to 1 volt. Find V naught. Find V naught. So we have a combination of NMOS and PMOS, right? Now, because now they have different W by L, but both MOSFETs are in series. What is the gate current here? The gate current is 0. No current is going to flow. So IDP is same as IDN. The clue is what? The current through PMOS is same as the current through NMOS. So from here, you can just substitute and do it, right? So what is IDP? It is mu Cox W by LP into VSG minus mod VT whole square by 2. But what is IDN? IDN, it's mu Cox W by Ln into VGS minus VT whole square by 2. So W by Ln equal to 2.5 W by LP. So please give me a substitution and solve this. By the way, what is VSG for PMOS? This is VS and this is VG. This is VGS, right? It is VS minus VG, which is 3 minus V naught. For NMOS, what is VGS for NMOS? VG minus VS. VG minus VS. VS is 0, VG is V naught. V naught minus 0 is V naught. So everything I've given, just substitute, that's it. Substitute and give me the answer quickly. So let me cancel mu and Cox. 2 also gets cancelled. So what is W by L N by W by L P? It's going to be 2.5, is it not? So what is VSG? VSG 3 minus V naught minus, what is VT? How much is VT? It is 1 whole square equal to, or W by L N by W by L P is going to be 2.5 into VGS minus VT whole square. VGS is V naught. V naught minus 1 whole square. So from here you have to find V naught. Okay. So my mathematics stops here, right? So you have to do it, and let me see in the comment section. If I have more answers for the same value, then I'll. So 1.387. 1.387. So the some students are saying 1.387. So I'll take it 1.39 volt. Very good. We'll have 1.39, right? So is it true that between 0 and 3, you get 1.39 in the middle? Yeah, possible. Is it not? Good. So your answer should be between 0 and 3 volts, 1.39. Okay, so there are many students who said 1.387. Very good. I'll go with that value. Now let's solve a gate problem. The examiner said that he has two MOSFETs and he has given 2 volt here. There's some voltage, say 10 volt. And he says that given your V0 is less than 1 volt, your V0 is less than 1 volt, and W by L2 is 2 times of W by L1, and your VT of course is 1 volt. 1 volt. Find V0. Find V0. So the examiner is trying to say, specifically say that your V0 is less than 1 volt. So give me a voltage that is less than 1. Give me a voltage that is less than 1. Obviously 0.5 would be coming to your mind, right? So if this is 0.5, what happens if V0 is 0.5? So your VDS is very small and your VGS minus VT, your VGS is already 2 here. So VGS minus VT is 1. So if your VGS minus VT is greater than VDS, so M1 transistor is going to be in triode and M2 is going to be in what region? Saturation. M2 is going to be in saturation. So given V0 is less than 1 volt or VDS1 is less than 1 volt. And what is VGS1? Minus VT, that is 2 minus 0. VGS is 2 minus 0, VT is 1. So it is 2 volt. So VGS1 minus VT is greater than VDS1. That means M1 is in triode. If M1 is in triode, your V0 is less than 1 volt. What is VDS2? VDS2 is 10 minus V0. So this is very large. Very large. So M2 is in saturation. So your VDS2 is very large, right? So M2 is in saturation. So M1 is in triode, right? So let me give you the values now. What is VGS1? VGS1. VG1 minus VS1, right? This is VG1. This is VS1. 2 minus 0, it's 2. What is VGS2? VGS2. It is VG2. VG2 and VG1 both are same. Minus VS2. It is 2 minus V0. Right? What is VDS2? VDS2 is VD2 or VDS1. What is VDS1? VD1 minus VS1. It is VDS1 is V0 minus 0 is V0. Am I right? And what is VDS2? It is VD2 minus VS2. It is 10 minus V0. So I'm just giving you, right? So it's simple. So all these values are there, but it is said that your M1 is in saturation and M1 is in triode and M2 is in saturation, right? But please, whether they are PMOS, NMOS, triode, saturation, it doesn't matter. If they are in series, then their currents are going to be same. But if they are in parallel, their voltages are going to be same, right? So tell me, ID1 equal to ID2. Why it is same? Because they are in series. They are in series. Am I right? But M1 is in triode. M1 is in triode. So tell me, what is the triode equation? Mu Cox W by L1 into VGS minus VT into VDS minus VDS square by 2. This is M1. What is M2? Mu Cox W by L into VGS2 minus VT whole square by 2. Whole square by 2, right? So let's give a substitution now. Mu cancel. Yeah, these guys get cancelled. So what is W by L1 by W by L2? W by L1 by, or W by L2 by W by L1 is going to be 2. So here I'm going to write 2 here, because W by L2 by W by L1 is going to be 2. Now what is VGS2? VGS2, second one, VGS2 is 2 minus, yeah, I've written it here, right? VGS2 is 2 minus V naught minus, what is VT? VT is 1 volt, whole square by 2, right? And what is VGS1? VGS1 is 2. 2 minus 1. VT is 1. VDS 1 is going to be V naught minus V naught square by 2. Okay. So, and why did I put an extra 2 here? Because W by L2 by W by L1. W by L2 by W by L1 is 2. So this is the equation we got, right? So give me V naught. Give me V naught. Come on, give me V naught. What is V naught? Okay. Okay, so Prashant and Dharmaraj, they say it's 0.422, 0.422, 0.422. Okay, Rajesh, so 0.422, Siddharth, Manasa, right? Good, 0.422. And I don't know, my mathematics is, when I've done this problem, I got some equation like this. Am I right? Just see, because you already got the answer. I got some equation like 3Vx square minus 6Vx plus 2 equal to 0. When I solve for Vx, the quadratic equation, right? So the Vx, I got two values, 1.577 and 0.422. So from here, I realized that my answer, the examiner, the gate examiner said it should be less than 1 volt. So 0.422 is absolutely right. Good job. Okay. Do everybody agree with 0.222? Okay, so everybody agree with that? Fine, we'll take that value. Okay, so far so good. Given mu Cox W by L is 1 milliampere per volt square. 1 milliampere per volt square. Vt is 1 volt. Vt is 1 volt. Find Vg, Vs and Vd. And of course Id also. So this looks like a voltage divider bias, but this is much more sophisticated than the voltage divider. What is the reason? Because the gate current, the base current is 0. So the device looks very stiff here. So you can see here, the Ig here is 0. So now you can confidently say that your Vg is going to be half of the 10 volt. So your Vg is directly 5 volt. Am I right? Please solve this. Okay, so let me solve this because of the voltage divider. What is VG? It is 10 into 100K by 100K plus 100K. Because of voltage division, this is going to be 5 volt. So how does the circuit change now? So what is VGS? It is going to be VG minus VS. It is 5 minus VS. VGS is 5 minus V. And what is ID? ID is simply VS by 6K. ID is VS by 6K. I'm just writing VGS and ID in terms of VS, right? Okay, but what is the equation ID? ID equal to mu Cox W by L VGS minus VT whole square by 2. So we are assuming what region? Saturation, right? Simple assumption, saturation. What is ID? ID is VS by 6K and mu Cox W by L is 1 milliampere. VGS is 5 minus VS and VT is 1 volt whole square by 2. So now we can find VS, right? Okay, so what is ID by Ohm's law? ID equal to VS minus 0 by 6K. What is ID? VS minus 0 by 6. Or what is ID? The same ID you can even write it as 10 minus VD by 6K. 10 minus VD by 6K, right? Your wish. ID is VS minus 0 by 6K or ID is 10 minus VD by 6K. So I'm writing VS because everything in terms of VS so that we can easily solve for VS. What is VS? Okay. So a student is saying that 2 minus 1 is 1, not 2. Okay, 2 minus 1 is 1. So 2 minus 1 is 1. Okay. It's still the same. Good catch. Okay, so what is VS? What is VS then? I got VS equal to 3 volts and 5.33. Now tell me which one is true? 3 volt and 5.33. Which one can be true? What if I take 5.33? Your VS is 5.33 volt. If your VS is 5.33, that means VS is the voltage across 6K. If the voltage across 6K is 5.33, then the above resistor 6K will also have 5.33. What is 5.33 plus 5.33? It's 10.66. But the power supply is only 10. When your VCC is 10, can you get a 10.66 drop across resistors? So it's not possible, right? So out of this makes no physical sense. Because 5.33 by 6K, you can take the current and multiply it by 6K plus 6K. So if across 6K there's 5.33, across this 6K also will be 5.33. So it's not possible. 3 volts is possible, right? So therefore, Vs equal to 3 volts. If your Vs is 3, what is ID? ID is Vs by 6K. 3 by 6K is going to be how much? 0.5 milli. 0.5 milli, right? And what is your VD? VD is 10 minus ID into 6K. It is 10 minus 0.5 into 6K. It is going to be 7 volt, right? So let me check whether our assumption is correct or not. Here I'm having 5 volt. Here I'm having 3 volt. Here I'm having 7 volt, right? So 5 minus 3 is 2, but 7 minus 3 is 4. So VDS is greater than VGS minus VT. So this is in what region? Saturation. Our assumption is correct. And these are the correct numbers. VD is 3 and VD is 7 and VS is 3. Very good. Or as a homework, you can do, you write everything in terms of ID. You can write everything in terms of ID or everything. Are you getting? It's not that I made it in terms of VS. I made it in terms of VS. So ID is VS by 6K and VGS is also in terms of VS. So we were able to find VS first. Okay. Now the same PNP and NPN combination we have also seen in BJT. And in BJT, we have seen these kind of structures. See, these kind of structures are very popular when we go for amplifiers like the differential amplifier. Amplifiers like what amplifier? Differential. If you connect a small signal at VG, then it becomes an amplifier. We will see that in differential amplifier, but this is only the biasing part. The biasing part of the differential amplifier. Are you getting? So what is the biasing part of the, please never bias a differential amplifier like this, right? If one transistor is on, the other is off, don't paralyze it. The best way to bias a differential amplifier is, right, both MOSFETs should be on. Both MOSFETs should be on and the current should divide into 2 equal parts. The current has to divide it into 2 equal parts. So that's the good way of biasing differential structures. Differential amplifier we will see later, but right now I'm not calling it like differential amplifier. In BJT you would have seen, I simply said 2 diodes. 2 diodes experience same potential difference. What will happen? The current has to get divided into 2 equal parts. Are you getting? So that's the DC part. AC we will see later, right? Okay. Okay. Now, so far so good. So some idea we have as to how to handle a BJT in DC as well as a MOSFET in DC, right? Now we'll go for AC analysis. We'll go for AC analysis. So this is exactly what we have done with diode. First, we have done all the diode problems using DC. And then we went for the small signal model. We went for small signal model. Small signal model of BJT. We went for small signal model of BJT, right? That means we are doing what analysis? AC analysis. Small signal model of the BJT. But to draw the small signal model, first class I told you, we have to know few fluctuations, right? So when my AC means it's a fluctuation of voltage and current. So when my VB fluctuates, how my IC is going to fluctuate. You can write small letters. I told you capital letters are for fixed voltages and small letters is for the fluctuation of voltages and currents, right? The change in voltage. So when my VB fluctuates, how my IC fluctuates, and here you have a VC and this is IB. Am I right? Right? So tell me, what is the relationship between VB and IC and IB? That's what we started, right? Fluctuation between IB and IC. IB and IC. So who is going to relate the fluctuation between IB and IC? Beta, right? What is beta? Beta is the short circuit current gain. Beta is defined as the short circuit current gain. So what is beta? It is IC by IB when VC is 0. So beta says that you take a BJT here and you short in here and inject a current IC and there's a current IB here, right? Your VC is 0. So beta is the largest gain that you get, right? The device gain, right? It's called the maximum gain. It's called the short circuit current gain. IC by IB when VC is 0, that is beta, right? IC by IB, the change in current by the change in voltage. And please, beta DC is same as beta AC. Why beta DC is same as beta AC? DC, I don't know. See here, suppose if somebody says, sir, capital IC is beta times of IB and small IC is also beta times, I don't know how to explain this. But what I can say is, if you have Y equal to MX, remember Y by X is M, right? So your Y by X is M, but your dy by dx is also M, right? So your dy by dx is also M. So beta AC and beta DC, they're almost same. Whether you call it IC by IB or you call it DIC by DIB, which is small IC by small IB, right? When I say small IC, it is DIC by DIB. Are you getting, right? So AC voltage, AC currents, IC and IB are related with beta DC and beta. That is why the examiner, if he gives beta 100, you can use that 100 for DC analysis and you can use that 100 also for what analysis? AC analysis, because my DIC by DIB, which is small IC by small IB, is also beta, right? Okay. What about the fluctuation of IC and VB? IC and VB, defining transconductance. Transconductance of the BJT. This is denoted by GM. This is denoted by what? GM. And what is GM? GM is the short circuit transconductance. Short circuit transconductance. And what this GM is going to relate, it's going to relate IC with VB. It is going to relate IC with VB. This is going to relate whom? IC with IB. IC with IB. is going to relate IC with VB. So let me define GM. GM is given as change in IC by change in VB. Change in IC with change in VB, right? Of course, the same VC is 0, short circuit. So here I'm having a transistor. This is IC and this is VB. IC by VB is the short circuit transconductance. But what is this value? How do you find this value? Beta is given by examiner, but what is GM? How do you find GM? What is GM? We know that IC equal to IS into e power VB by VT. So what is GM? It is DIC by dVB, which is small IC by VB, small VB, right? Change in IC by change in VB, right? So if you differentiate, what do you get? IS into e power VB by VT into 1 by VT. I think this we have done in diode also. So if my VB is on x-axis and IC is on y-axis, and I'm choosing an operating point somewhere here, here I'm applying a small signal, then this is my gain that I get. So the slope is your GM, right? The slope is the slope. Small VB, the small IC, right? So GM is nothing but the slope of the characteristic. What is slope formula in mathematics? Change of y by change of x, small IC by small VB. And how much is that DC that I told you? This capital VB DC. This is 700 millivolt, right? 0.7 volts. 0.7 volts. So please, when I say VB here, this is 700 millivolt plus 1 millivolt. So if I have a 1 millivolt signal, then it is 700 millivolt plus 1 millivolt. This is almost 700. IS into e power VB by VT into 1 by VT. So this is equal to IC DC by VT. So let me, this is very, very important. For all gate problems, what is GM? It is IC DC by VT. The DC operating point is going to decide the transconductance of the device, transconductance, right? This is, of course, the change, the fluctuation in IC with the fluctuation in VB. So when my VB changes, my IC will change by what amount? Somebody asks you, if I'm changing my VB, how much it will, by what amount my IC will change? Then what you have to say? You have to tell them that what is the operating current? If the operating current is 1 milliampere and your VT is 25 millivolt, the change is going to be 1 by 25. 1 by 25 will be the change between IC and the fluctuations between IC and VB, right? So GM is called the transconductance. Strictly short circuit transconductance, but we'll call it transconductance of the BJT. So this is my second fluctuation. My first fluctuation is between whom? IC and IB. The second fluctuation is between IC and VB, right? This is very important. GM, what is the value of GM? The value of GM is going to be IC DC by VT. IC DC by VT. And the proof for this is this. This is the proof for IC by VT. So how do I prove this? This is my second fluctuation. So you're applying a small signal at the operating point, and the slope is nothing but the transconductance. Now, what are the other fluctuations we have? VB and IB is also there. My third this is the fluctuations between VB and IB. The fluctuation between the VB and IB. So defining the base to emitter resistance, base to emitter resistance. This in books is called as R pi, which is VB by IB. So I'm going to model this transistor with a resistor here, with a resistor. This is VB and this IB. VB by IB, I'm going to replace this port, right? The base and emitter with a resistor here, between the 2 points. I'm going to connect the resistor. But what is that value of that resistor? That resistance value is going to tell you the fluctuations between VB and IB, how VB changes with IB. So VB, can I write IB as IC by beta? IC by beta. So this is going to be beta by IC by VB. Now just now I wrote what is IC by VB. What is IC by VB here? IC by VB here, you can know that it is the transconductance GM. So this is going to be beta by GM. So the value of beta by GM is going to tell you, so when in a common emitter amplifier, when I give a BJT and a signal is applied and the VB fluctuates with IB because of the signal, right? When my signal changes, my VB changes, my IB, that fluctuation between the VB and IB is modeled as a resistor, and that resistance value is going to be beta by GM. It's going to be what? Beta by GM. So three fluctuations are there. Fluctuation between IB and IC, transconductance of the BJT, which is the fluctuations between VB and IC, and the third fluctuation is between the VB and IB. VB and IB, that is R pi, right? So far so good. With these three, we can model the BJT, but if you want, we can have the fourth fluctuation, which is the early effect. Early effect, right? So the early effect relates IC with VB. How IC changes with VB. So this is something we have seen so many times. Sorry, IC with VC. So this we have seen so many times, right? So I've drawn characteristics like this. And then the slope will actually tell you the relationship between delta VC when you apply a small signal with delta IC. So how did we found the slope of this triangle? I think we extended this line. Do you remember? We extended this line and we call this as what voltage? Early voltage. So tell me, what is R0? R0 is going to be delta VC by delta IC, which is small VC by small IC, change in VC. What is this value here? The value, this I have already proved it to be early voltage by ICDC. Early voltage by ICDC, right? So this R0 tells you the fluctuations between IC and VC. IC and VC. IC and VC. IC and VC. Okay. Now you tell me, when I apply a signal and there's so many fluctuations that are going on, where VB changes, IB changes, and then IC changes with VC, there's so many things that are going on, right? And how do we model all those fluctuations of the BJT, right? So what model will you propose? The model is, here my VB is changing with IB. This I'm going to model with a resistor here. With a resistor, this is VB here and IB. And what is VB by IB? What is VB by IB? Here, R pi. So I'm going to put R pi here. And this value of resistance will tell me the fluctuation between VB and IB. And what is IC? I have given you IC two relations. Any one you can use. Any one you can use. Your IC will relate with VB or IC will relate with IB. Suppose if your IC relates with VB, you can write it in this fashion. You can write it in this fashion. Your IC is relating with VB. So what model will you draw here? What model are you going to draw here? Your IC with VB and IC with VC. What model are you going to draw here? Input, you have given some signal, but output there is a current. And what model are you going to draw here? Can we have a, I don't know, can we have some sort of a Norton model or something? Norton or Thevenin, your wish, right? So how do you propose a Norton model? What is a Norton model? A Norton model says that if I'm having a BJT, then I should have a short circuited current and the output resistance here are short circuit, right? So the Norton model says that I should have a current I Norton, which is a short circuited current, in parallel with some resistance RSC here, right? So that's the model of the BJT. But I told you this is my IC, right? This is my IC. So what's the relationship between my short circuited current and IC? Oh, they are opposite, right? So this opposite. So can I write it minus IC like this, minus IC. And what is IC? IC is GM times of VB, because IC by VB is GM. So IC is GM times of VB. So this negative symbol is a big headache, right? This negative symbol is a big headache. What is RC? It is the fluctuations between VC and IC. So this is your R0. Okay. But how do I remove this negative sign? Any suggestion how I'm going to remove that negative sign? To remove that negative sign, can I reverse the current source polarity? Can I reverse the current source polarity, right? So I'm going to draw it like this here, the small signal model. Here there is VB and IB. So this I'm going to equate it with a resistor, right? So this is something I'm applying, VB and IB. So here you have R pi. And what is a Norton model you're going to propose at the output? At the output, there is a IC here and your VC here. So it's better that I reverse the current source here, reverse it like this. If I put an arrow down, I can write GMVB. And the Norton's resistance, I can put it here as R0 here, right? So this becomes this is my base terminal, emitter terminal, and collector terminal. This is the Norton model or the pi model, the Norton model or the pi model. So this model, if you use in the place of BJT, and when you apply the signal, there's so many fluctuations that are going on. This R pi relates the fluctuation between VB and IB. The GMVB is the fluctuation between what? IC and VB, and R0 is the fluctuation between IC and VC. So everything is included here. This is the exact BJT behavior. If you take an exact BJT in the lab, whatever answer that BJT is going to give, this model is almost going to give you almost 95, 98%. This is going to give you the same answer. But if you say that, is this the same which mimics the exact BJT? No. A VLSI tool has 42 elements like this. 42 elements. They have noise modeling and all that. So there'll be 42 elements in a VLSI tool. And finally, they say that this is the exact BJT. But human beings, we cannot do that. In fact, if you ask me, most of the gate problems, they don't have early effect. When they don't have early effect, what is a model in most of the gate problems? This is with early effect, small signal model. Without early effect, small signal model. Neglecting early effect. Neglecting early effect. So if you neglect early effect, that means your VA is infinite or your R0 is infinite, because R0 is VA by ICDC, right? So your R naught is infinite. So if you see most of the gate problems, they have this model. They simply say that there is an R pi here, which relates the fluctuations between VB and IB, and your IC is going to be GM times of VB. That's all, GM times of VB. So this is a very, very popular model. Of course, I'll do both. First, I'll include without early effect, and then I'm going to include with early effect. This is pi model neglecting early effect. This is the pi model neglecting what effect? Early effect. So what is the summary of the discussion? Finally, the summary of the discussion is a student should know this model, right? This model. And please, what are the values which he should remember? The summary is this. You should remember this model. What is R pi? Beta by GM. What is GM? IC by VT. IC by VT. And what is R naught? Early voltage by ICDC. So this is the summary of the discussion, right? So you should remember all the three numbers. So if you replace, they are going to explain the fluctuations between the voltages and currents in the BJT. So when you apply a signal, and if you take a microphone and connect it at the base or emitter, and you start saying hello, hello like that, so the transducer output is going to have a change, and that change is going to create a change in the BJT terminals. So that those fluctuations are these values. These values will tell the first value tells how VB changes with IB. The second one tells how IC is going to fluctuate with VB, right? And the last one, R naught, is going to tell how IC is going to fluctuate with VC. But if you ask me, sir, how is that these fluctuations are individual, right? They all fluctuate at the same time, but we are taking it individually. That's the beauty of superposition, right? Superposition says that if the response is kind of is the total response due to 3 is always the summation of individual responses, right? And now if you ask me, sir, how you can add all the responses and have a model, something like this, Yes, because the signal is kept small. If you kept small signal, then if as long as the signal is kept small, the device is going to be linear and it is going to follow the linearity property, right? Or superposition. That's okay, right? So experimentally, they have proved that the theoretical answer is going to match with the practical application. So whatever you do on paper is going to match with what you see in the lab, right? So that's a good sigh of relief, right? We're doing something here and the same thing is expected in the lab. So that's the beauty of this model, right? Okay. Okay. Now tell me, what is the first configuration we are going to take? Configurations of BJT. Configurations of BJT. What are the configurations we have? CE, CB, and CC. CE, CB, and CC. CE stands for, what is CB? CB means what? Chicken biryani. What is CB? Common base amplifier. CE is common emitter and CC is common collector, right? So we'll take the common emitter first. We'll take the common emitter first and solve it. So let's use this model. This is a very simplest model, right? Calculate AV, V0 by Vin, AI, Rin, R0 for the CE amplifier given. CE amplifier given, beta is 100, VB on is 0.7, and VT or VA is infinite. When I say VA infinite, neglect early effect. And VT you can take 26 or 25 millivolt. 25 millivolt, right? Just for simplicity, I'm giving a biasing voltage of 2.7 volt. Now please see the small signal analysis of a diode. The same procedure we are going to apply now, right? So this is what amplifier? CE amplifier, CE amplifier. Right? CE amplifier or common emitter amplifier. Common emitter amplifier. Common emitter, right? So tell me, what are the three configurations we have? The word CE, CB, CC is related only to AC analysis. This is only AC analysis, not DC. In AC analysis, if your BJT looks like this, input here, output here, emitter is grounded. If emitter is grounded in AC analysis, we call it CE. CE. What is common? Emitter is common to both input and output. That is called CE, right? Common emitter in AC analysis. There is one more configuration. If base is grounded, input is given here, output is taken here, then it is called CB amplifier. CB. Why CB? Because what is common to both input and output is the base terminal. If the base is grounded, then we call it common base, right? So three configurations we are going to see. And who is the last guy? CC, common collector. In a common collector amplifier, input is given at base, output is taken at emitter, and collector should be grounded, right? So the collector is common. So there are three configurations we are going to see: CE, CB, and CC. So what happens in, see, BJT is such a wonderful device. If you keep changing the input and the output positions, you're going to have completely different characteristics, right, of the device, right? When you see through base terminal, you have R pi. We have seen that. But if you see through emitter terminal and inject an emitter current, then there is no base current. The current increases. When the current increases, the resistance will decrease. If current decreases, resistance will increase. According to Ohm's law, what is R? R equal to V by I. R equal to V by I. If I is base current, then the resistance will be very large. So the resistance is large when you see through base terminal. But if you see through emitter terminal, I is large. So naturally, the current is going to be, the resistance is going to be less. So same BJT, but a common base amplifier will give you low resistance because the input is given at emitter. But the common emitter amplifier or common collector amplifier, they're going to give slightly high as compared with common base because your input is given at the base terminal. It's simple logic. So we are going to see that step by step. First, we are going to see common emitter amplifier. Just refer to your previous pages of small signal analysis. How did we do small signal analysis of diode? First, we have to do DC analysis. Then we have to go for what analysis? AC analysis. First DC and then go for AC, right? So let's start the solution. DC analysis. For DC analysis, what should I do to AC source? V in source should be short circuited. Capacitors should be short circuited. Capacitors should be, what is capacitor? Open circuited. What is the frequency of DC? F equal to 0 for DC. So what is the impedance offered by capacitor? 1 by omega C or 1 by 2 pi FC. So the frequency is 0. This is infinite. So capacitor offers large impedance for DC, large impedance. So capacitor should be replaced by open circuit and V in should be replaced with short circuit, right? Yeah. Now tell me, what is your IE now? IE. Don't forget the procedure. What is VE first? VE. Tell me what is VE? VE equal to 2.7 minus 0.7, that is 2. IE is VE by 2K. It is 1 milliampere. IC, beta by beta plus 1 times of IE. Do you remember all this, right? 100 by 101 times 1 milli. That is going to be 0.99 milli, right? Is your IC. Now, this is your operating current. This is your operating current. From here, how do we get AC analysis? How do we get AC analysis, right? For getting AC analysis, tell me what is GM. GM is IC by VT. 0.99 milli by 25 millivolt. This is GM, right? And what is R pi? Beta by GM. Beta is 100, GM is 0.99 by 25. It is approximately 2.5 K. 2.5 K. Are you getting? So what is the small signal model? Small signal model. The small signal model can be like this. Here you have R pi, here GMVB. This is VB. 2.5 K. What is GM? 0.99 milli by 25 milli into VB, right? Or if you see, if you don't like GMVB as IC, what is the first fluctuation I've given you? IC also relates with IB, I told you, am I right? So you can do like this, or I will do both. When I'm doing it intuitively, I'll do only by this. But if somebody is not comfortable with 0.99 like that, then he can do one thing. The GMVB, he can even write it as beta IB also. So one and the same. So BJT is modeled as a current controlled current source here. What is beta? 100 IB. Both are same, right? So you can have GMVB or beta IB, your wish. So let me prove it. IC equal to beta IB, or it is GMVB. All right. So how to prove that both are same? What is IB? IB can be written as what? VB by R pi. Am I right? So this is nothing but beta times of IB is nothing but VB by R pi. What is R pi? R pi is beta by GM. So this is nothing but GMVB. Okay, LHS equal to RHS, something like that. Are you getting? We took an LHS and we proved it. So your wish, you can take GMVB or beta IB, your wish, right? Your answer is not going to change. So let me repeat it once again. Like the diode problem, first we have to do DC analysis and calculate the DC operating current. After getting DC operating current, you can find GM and R pi. Then you have this small signal model. Small signal model. Now you can go for AC analysis. AC analysis. For AC analysis, your frequency is high, mid-frequency range high. You have to short circuit VCC. VCC, DC sources should be short circuited, and capacitors also to be replaced by short circuit. What is the impedance offered by capacitor? 1 by 2 pi FC. F is high, this is 0. Capacitor offers low impedance for AC. See, all of you, do you remember capacitor blocks DC and allows AC? Yes or no? He will block DC. Block means what? He acts as an open circuit and charges to the potential difference. Allow AC, he will act like a short circuit for AC analysis. So I'm having a BJT here. Capacitor is replaced by short. And here you have VCC, 10 volt. How do you short circuit source? How do you short circuit source? You have to short these 2 points, am I right? Then this point is connected to ground. Here, the DC shorted, you are having only the signal. So let me name the nodes here. This is node 1, 1, 1, 1. This is also 1. All right. This is 1. They're all same ground. This is 2 and 3. There are 3 nodes. I think it's better we write it like this. This is ground. And here, this is 3. So we can have a 3K here as a load, where you take the output with respect to ground, and input is V. Can you see? This is exactly what I told you as common emitter when I started the CL. So what is a common emitter? The word common refers to AC analysis. So when you draw AC analysis, you should have a clean circuit like this. So what is this circuit? Input should be given at base, output should be taken at collector, and emitter is grounded. Input is given at base, output is taken at collector, and emitter is grounded. This is a clean common emitter amplifier, right? And in diode, what did you do? This transistor is replaced by the small signal model. Small signal model is replaced by what model? Small signal. So here you have R pi. Here there is GM V pi or VB or beta IB, your wish. And here you are connecting a small signal V in. There is 3K or RL or RC. And what is the value of this? 2.5K. 2.5. This is 0.99 by 25. Base, emitter, collector. Emitter is grounded. See how simple the circuit is. If you know how to solve this, then you know how to solve the common emitter. If you know how to solve this, then you know how to solve the common emitter. Am I right? So which one is easy to calculate? Which one is easy to calculate? First, let us calculate the gain or the input resistance, right? What is the input resistance of the amplifier? Rin. Tell me. Defining input resistance of amplifier. What is input resistance of any amplifier? It is V in by I in. V in by I in. So V in is VB, I in is IB. Tell me, by Ohm's law, what is V by I? VB by IB is nothing but R. This is R pi. 2.5K. 2.5K. So this is the input resistance of the common emitter amplifier, right? So first parameter is over. Second parameter, if this current is GMVB, what is the current in opposite? Opposite V0 is minus GMVB into RC. And V in is directly VB. V in is directly VB. So defining voltage gain. Voltage gain is denoted by AV, which is V0 by V. VB cancel minus GMRC. So this is very, very popular, very, very important, right? You should almost like, it's a student should by heart the voltage gain of a common emitter minus GM into RC, minus of the short circuit transconductance into RC. So you can have a value here minus 0.99 by 25 and RC is 3K. So somebody with a calculator can help me with that 0.99 by 25 and 3K, right? R5 we know, R5 is 2.5K. So this is the second parameter. Now, what is the third parameter? Suppose if this is the load current IL, defining current gain. What is current gain AI? It is IL by IN. IL is minus IC, IN is IB. What is IC by IB? Beta, so it's 100. It is 100. Now please, what does this negative sign indicate? All of you, what does this negative sign indicate? The negative sign indicates that what is V0 by Vin equal to? What is that value? Minus 0.99 by 25 into 3K. What is 0.99 by 25? That is 3000 by 25. How much is that? 3000 by 25. Approximately 25 goes 4 times 400. So 120. Am I right? 120. So 118.8. You're saying 118.8. Good. Now tell me, what does this negative sign indicate? Can you please sketch this 118.8 in your mind? How do you sketch? My V0 is minus 118.8 times of Vin. What do you mean by this? It means that if I give Vin like this, a small sine wave, it's going to get bigger by 118 times, but the negative sign indicates that the output is going to flip by 180 degrees. So what's that? The two things are here. The 118 indicates the magnitude of the magnitude, and the negative sign is going to indicate that it's going to flip by 180 degrees. So similarly, when I say my IC or my IL is minus 100 times of IN, what do you mean by that? What do you mean by that? If my IN is fluctuating like this, right? It's a fluctuating. It could be an audio signal, or it could be some sort of a signal, but I'm just taking a sine wave. So if I take a sine wave as my input, some audio signal, then my load current is going to increase by 100 times, but the negative sign indicates that it's going to flip by 180 degrees. So please remember, common emitter gives 180 degrees phase shift, both for voltage as well as for current, right? When I say voltage, I'm comparing Vin with V0. When I say current, I'm going to compare IN with IL, right? Okay, so the third one is the current gain. What is the last one? What is the last one? The output resistance of the amplifier. Output resistance. R0. For calculating output resistance, what should we do, right? So if suppose the examiner puts an arrow here, right? The arrow, it all depends on where he puts the arrow. Please see here, where is the arrow here for output resistance? Yeah, the arrow is down. Are you getting, whenever he puts an arrow down, what do you mean by that? See here, I have two resistors now, R1 and R2. And somebody puts an arrow here. What do you mean by that? It means that this arrow, when I inject a current, that current will divide between the two resistors. So I have to include R1 parallel with R2. This is R1, this is X, and from X there is R2 here. So my R0 indicates that it is R1 parallel with R2, both. But here I've included a transistor here and an RC here, RC, and I'm putting a arrow here. So it is understood that I have to include the transistor as well as RC, right? Okay, what happens if somebody puts an arrow only down like this? If the arrow is down, R01 and say R02, R01 is going to be R1, but R02 is going to be R1 parallel with R2, right? If he puts an arrow sidewise, you have to include both R1 and R2, right? So I've put sidewise, so you have to include RC also. So this is a transistor here, there's an RC here. Now you tell me, what is output resistance? It is RC. It is RC. But for calculating output resistance, what will you do to voltage sources? Short. Am I right? Oh, I forgot the model. Without the model, I'm drawing directly, because in the next topic, we're going to do this orally, right? Just by seeing, I'm going to make practice, right? Even if there are 2 transistors, 5 transistors, 10 transistors, just by looking at the amplifier, you have to write voltage gain, input resistance, output resistance, like that, by inspection. So let me put it here like this. So for calculating output resistance, tell me what we should do. What is the procedure I've given you in my first class? You have to short voltage source. Short voltage source. Connect 1 volt source at the output terminals. Find current I0 or Ix. By Ohm's law, R0 equal to 1 volt by Ix. Do you remember this? So please tell me, if you short your IB 0, right? Your IB is 0 or your VB is 0, then your GM VB is also 0. 0 current means open circuit. So you have only RC. You have only RC. Your Ix is going to be 1 volt by RC. 1 by Ix is RC. Output resistance is simply the collector. Please, thumb rule. In a common emitter, the output resistance is the collector resistance. Say it, right? Say it 10 times in your mind. In a common emitter, the output resistance is the collector resistance. The output resistance is the collector resistance, right? Say it 100 times in your mind. The output resistance is the collector resistance, RC, and that is 3K. That is 3K, right? If you see here, from here, then your output resistance is infinite. If you see from here, your output resistance is infinite. So minus 118 minus 100. Now tell me, what is the summary of common emitter? Summary. Moderate input resistance. Moderate input resistance. Rn equal to R pi. High voltage gain. High voltage gain. AV equal to minus GMRC. It's around minus 118. High current gain. High current gain. AI is approximately minus beta. And what does the negative sign indicate? 180 degrees phase shift of both voltage and current. Voltage and current. And moderate output resistance. Moderate output resistance. And all of you, very, very important. Why we go for common emitter? What is the major advantage of common emitter? This is the only amplifier which has both voltage gain and current gain. Very high power gain. Very high power gain. Please calculate power gain and tell me. AP equal to AV into AI. Minus 118 is almost 118.8, 119, and then minus 100. So it's 11900. 11,900 is the power gain of the common emitter, right? So this is the major advantage of common emitter amplifier. Tremendous power gain, tremendous power gain.
That when will your break come?
Okay, so this is the summary of common emitter. We'll take a break now. We'll take a break. When I come back, we will see the other two configurations, right? And please don't miss future classes, because we are going to do intuitively the common emitter. The first, when I've given the syllabus, right? I made a promise when I given the syllabus. I said we are going to do things intuitively, just by looking at the amplifier. We are going to calculate the gain, input resistance, output resistance, even if they are multiple transistors, right? So we'll do that. Take a break and come back. Okay, can you hear me? 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 Yes. Okay. So we have done the common emitter, right? So we have seen that the common emitter amplifier input resistance Rin is what? R pi. And your output resistance R0 is infinite. But if you take from here, your R0 is going to be RC. And the voltage gain, this is the voltage gain AV is going to be minus GM into RC. And the current gain AI is minus beta. All right. Okay. So this is where we stopped. Now let's go for the common. What are the other configurations? We go for the second configuration. Common collector. All of you, is there another name for common collector? What is the other name for common collector? What is the other name for common collector? Emitter follower. Very good, Harsha. Emitter follower for the emitter follower circuit. For the emitter follower circuit, calculate your AV, Rin and R0. VT is 25 millivolt. And what are the other things? VT is 25 milli and beta 100, VB on 0.7. And neglect early effect. Your early voltage is infinite. Emitter follower. Input is given at base. Output is taken at emitter. Right? And all of you, what is VCC for AC analysis? What is VCC for AC analysis? Your VCC for AC analysis is ground, right? So this VCC is also called signal ground. It's called signal ground, right? This VCC is also called signal ground. So that is the reason this is a common collector amplifier, because input is given at base, output is taken at emitter, and the collector is connected to a point where that point is called ground. See, please, from the signal point of view, who is ground, right? There's a signal here. And from this guy's point of view, who is ground? Who is ground, right? He thinks that any voltage that doesn't change is ground, right? Any dynamic, any point that's static and doesn't change is ground. Because for AC analysis, those points, with respect to those points, they will behave as if they are the ground node, right? So that's the difference between static and dynamic. So it's only about, it's not, from the signal point of view, any voltages that are static are nothing but what? A ground node, right? For AC analysis, all the DC voltages are short-circuited to ground. Remember that, right? And what are the other parameters we have to find? You have to calculate R in here, and you have to calculate R0 here. R in here and R0 here, right? But please, in the exam, the examiner will ask you only one parameter, right? Only one parameter, either Rn or R0 or AV, right? Or AI. Mostly AI is not at all a parameter, because if input is given at base and output is taken at emitter, then 1 plus beta is the current gain. If input is at base and the output current is at collector, it is beta. So current gain is not at all a parameter. So mostly parameters means AV, Rin and R naught, right? These three you have to focus. Fine. So one of them will be asked, but we will calculate all the parameters so that we can know the characteristics of an emitter follower. Emitter follower circuit is also called the common collector circuit. Common collector. It is also called the common collector. Okay. Shall we start now? Right. Tell me, what is the DC current? Yeah, your emitter follower is the like the voltage follower. Yeah, very good. Very good. Okay, so we'll start the DC analysis. So for DC analysis, your AC sources are short circuited, right? And even capacitors, if they are treated as open circuit. So tell me, what is VE? VE is minus 0.7. And what is IE? IE is minus 0.7 minus of minus 8.7 by 8K. That is still going to be 1 milliampere. So it's 1 milli. Then what is your IC/DC? What is your IC/DC? Your IE and IC both are same. IC is going to be beta by beta plus 1 times 1 milli. That is 0.99 milli. So this is the operating current. This is the operating current. Right? This is the operating current. So this is the operating current, right? Now, what is R pi? Beta by GM. Beta is 100. GM is IC by VT. It is 100 by 0.99 milli by 25 milli. This is approximately 2.5K. Same thing, right? And GM is going to be IC by VT. 0.99 milli by 25 milli. So what is the small signal model? You have 2.5K here. and this is GM times of VB. If there is a VB. Base, emitter, collector. So the AC model we have got from DC analysis. We have got from what analysis? DC analysis. And what if your IC is not 1 milliampere, but if it is 2 milliampere? If your IC is 2 milliampere, then your RPI is going to be 100 by 2 by 25. It's going to be 1.25K. Don't think RPI is always 2.5K. Why is RPI 2.5? Because your operating current is 1 milliampere. If your operating current is 2 milliampere, then it is going to be 1.25K, right? Now we can go for AC analysis. Your DC sources are shorted to ground. Shorted to ground. The DC sources are shorted to ground. Okay. So we'll go to the next page. The BJT is replaced with RPI, GMEB, let us make the connections now. You can see here from the emitter to ground, you have 8K. Right? This is like the emitter resistor RE, right? RE is 8K. From the base to ground, what do you have? You have V in. Base to ground, you have V in. So only two elements, right? One V in and 8K. Simple circuit. V in is there, 8K is there. And the connector is connected to ground node. So this is the dynamic equivalent of the BJT. right? And the dynamic equivalent of the whole amplifier. Static we have seen, DC analysis we have seen. So this is AC analysis. Oh, all of you, in the previous diagram, see here, the common emitter amplifier, which model did we use? I put GMVB here. So I thought just we'll do both. I said we'll do both and I forgot. Yeah, you do by GMVB. Can I write GMVB? What is the other thing I can write for GMVB? I told you we'll do both. GMVB can also be written as what? Beta IB. And did I prove that GMVB or beta IB are same? Yeah, right? So it's your wish. The first problem I've done with GMVB. Now I want to do with beta IB, right? So next problem again I'll do with GMVB. So we can finally we'll come to a conclusion that however you do, your answer is not going to change. So that to get that feeling, right? Okay. Okay, so which one shall we find now? Which one shall we find? If this is IB, this is beta IB, what is the effective current here? This is IB, this is beta IB. What is the total current? IB plus beta IB. It is IB plus beta IB. It is going to be 1 plus beta times of IB. 1 plus beta times of IB. So what is V naught? V naught is going to be 1 plus beta times of IB into 8K, which is RE. Which is RE, right? And what is V in? Give me a KVL in this loop. KVL. Minus V in plus IB into R pi plus 1 plus beta times of IB is a current into RE equal to 0. So what is V in? V in is going to be IB into R pi plus 1 plus beta times of RE. Defining voltage gain. Denoted by AV, V naught by V in. So what do you get? V naught by V in. IB cancel. 1 plus beta times of RE by R pi plus 1 plus beta times of RE. Now, if you say that, no, sir, I want to do with GMVB. So what answer is expected if you do with GMVB? Same thing, but your numerator and denominator will be divided by 1 by beta, or 1 plus beta. If you divide numerator and denominator by 1 plus beta, what will you get? RE plus R pi by 1 plus beta. What is R pi? R pi is beta by 1 plus beta by GM. So what is beta by beta, 1 plus beta by GM? Alpha by GM. So you're going to get alpha by GM. So two forms of voltage gain, right? So I'll tell you how to get a shortcut for this just by looking at the circuit. You should be able to tell the answer, right? So if you do by beta IB model, you're going to get 1 plus beta times of RE by R pi plus 1 plus beta times of RE, or RE by RE plus alpha by GM. Okay. What is alpha? Beta by beta plus 1 is alpha, right? Beta by 1 plus beta is nothing but alpha. I've already given this in DC analysis. Okay. Now, what are the numbers? We have calculated what are the numbers. Beta is 100. 101 into 8K by 2.5K plus 101 into 8K. Now, compared with compared with 101 into 8K, what is 2.5K? Very small. If you neglect 2.5K, 101 into 8K, 101 into 8K gets cancelled. This is almost 1, 0.999 or 998 you get. So what is the other name for emitter follower? Very good. Some of you have said it's a voltage follower. It's a voltage follower. The output is going to follow the input. That means this is having a gain 1. This is having a gain 1 voltage follower or emitter follower, right? The gain is 0.88998. So what do you mean by this? If I give an input V in here, my V naught is approximately 0.998 V or approximately V. Approximately V. So what do you mean by this? The output at emitter follows input at base. The output at emitter follows the input, right? Input is all, of course, it's given at base only. The output at emitter follows input, right? That is why it is called, this is the reason the circuit is named as an emitter follower. It's called an emitter follower. The output at emitter follows the input. The output at emitter follows the input. That is why it is called an emitter follower. And you said voltage follower. Yes, the gain of this follower is 1. So that is why it is also called voltage follower, or also called voltage buffer. Why is it called a buffer? Because its gain is 1. Its gain is 1. But that doesn't qualify to be called as a buffer. So if a good buffer, voltage buffer, I told you, should have impedance matching, right? It should have high input resistance and low output resistance. High low is VCVS. Low high is CCCS. High high is transconductance. Low low is trans resistance. So if somebody says this is a good voltage buffer, then what about the input and output resistance? Should have high input resistance and low output resistance. You should have high input resistance and low output resistance, right? Okay, go to the next page. Now, if this current is I in, what is the input resistance of this amplifier R in? Input resistance. It is going to be V in by I in. It is going to be V in by I in. It is going to be V in by I in. So tell me, what is V in? V in is IB into, we already derived this, R pi plus 1 plus beta times of R. R pi plus, so the equation is here from equation 2. Equation 2. Right? So IB is nothing but I in. IB is nothing but I in into R pi plus 1 plus beta times of R. So defining input resistance. Input resistance is R pi, which is V in by I in. So what is V in by I in? It is R pi plus 1 plus beta times of R. Am I right? This R in. R pi plus 1 plus beta times of R. And it is 2.5K plus 1 plus 100 into 8K. 1 plus 100 into 8K. Beta is 100. So this is input resistance. What is this value? 101 into 8K plus this value. What is the value? 810.5K. Okay. So this is approximately 810K. So somebody is saying 810K. So it's like 0.8 mega ohm, right? 810K, 0.8 mega, approximately 0.8 mega ohm. So that's a big number, almost 1 mega ohm, right? Input resistance. What about current gain? This is simple. Current gain AI is some current IL by IN. The load current here to this 8K is going to be 1 plus beta times of IB, and IN is IB. IB cancel. 1 plus beta, it is 101. Beta is 100, right? 101. 101. 1 plus beta. So this is the current gain. So I think all the parameters are done. Oh, we are left with output resistance, right? The voltage gain is done. It's got 1. Input resistance is quite high, right? At least in common emitter, we had R-pi, which is 2.5K, but here it is R-pi plus 1 plus beta times of RE, and the current gain is 101. So how do we calculate the output resistance of the amplifier? Output resistance. But in exam, only one parameter will be asked. For example, input resistance. So you can simply say that it is V in by IB, R pi plus 1 plus beta times of RE. That's 2 marks. But now we are calculating all the parameters, right? Okay, we'll go to the next page now. Output resistance or not. How do we calculate output resistance? For calculating output resistance, I told you, if you're finding, if the arrow is here, you have to collect 1 volt source here, find current drawn, Ix or I naught. By Ohm's law, 1 volt by Ix is the output resistance. But before that, what should I do to voltage sources here? There is a voltage source here. I have to replace it by short. And collector is already shorted to ground. Okay, so what is that current Ix? If this node is 1 volt, this node is also 1. Am I right? Am I right? Okay, if this is ground, what is the voltage of ground? What's the voltage of ground? That's 0. So this is ground, and this is ground. So it's 0. So here you have 1 volt here, 1 volt, and there is an IB flowing. So what is IB because of this 1 volt? IB equal to zero minus 1 by R pi. Minus 1 by R pi. IB is 0 minus 1 by R pi. Am I right? And what is this current here? IX, and what is IY? What is IY? IY is equal to 1 minus 0 by RE. It is 1 by RE. Okay, so every current we know, right? Every branch current we know. Oh my God, it's in the middle. Okay. Yeah. So IB is known, IY is known. Just tell me KCL at this node. Entering, and leaving. So there are 3 currents entering. IB plus beta IB is entering, plus IX is entering, and IY is leaving. So there are 3 currents entering this node, and only 1 current is leaving. So what are entering? IB plus beta IB. So it is 1 plus beta times of IB. What is IB? Minus 1 by R pi. Plus IX is 1 by RE. So what is IX? It is 1 by RE plus 1 plus beta times by R pi. Am I right? So what is R naught? R naught is 1 by IX. It is going to be 1 by RE plus 1 by R pi by 1 plus beta. R pi by 1 plus beta, I just now wrote it is alpha by GM. Right? So see, this is something like your parallel resistors formula, right? So what is the like a parallel 1 by R1 and 1 by R2, 1 by, so this is, what is this in your networks? This is a basic formula you have learned in 10th standard, right? R1 parallel with R2. So this is like your RE parallel with R pi by 1 plus beta, which is alpha by GM, right? R pi, RE parallel with 1 by beta, or RE parallel with alpha by GM. Okay, because R pi is beta by beta plus 1. Okay, so what is the value? Answer. We need answer, right? I'm just deriving so that, but we need answer. What is the answer for R naught? It is 1 by 8K plus 1 by 8K plus 1 plus beta, 101 by R pi. What is R pi? 2.5K. Yeah, somebody can give me an answer for this. It is 2.5 by 100. It's 25 ohms. So 25 parallel with 8. $25 parallel with 8K. How much? It's 25 ohms. Okay. 24. Somebody's saying 24.67. They're saying 24.67. Okay. So low output resistance. Okay, so what is the summary of common collector? Summary. Tell me what is the summary? High input resistance, almost 0.8 mega ohm, and low output resistance. Low output resistance. So high input resistance, the amplifier is voltage controlled. It takes the signal in voltage form, voltage control. Low output resistance, the amplifier is a voltage source, right? Voltage control voltage source. So CC amplifier is a VCVS. It is what? VCVS, voltage control voltage source, means high low is VCVS, low high CCCS, high high transconductance, low low trans resistance. The voltage gain is approximately 1. That is why we call this as a voltage buffer, right? Or VCVS, high current gain, high current gain. What is the power gain? AP, AV into AI. But because your AI is 1, your power gain is AV is 1, power gain is only AI, right? And did you observe any negative sign? Did you observe any negative sign in the voltage gain and current gain? Current gain is 101, voltage gain is 0.99. So no phase shift. No phase shift of both voltage and current. No phase shift of both voltage and current. So this is the characteristics of a common collector amplifier, a CC amplifier, or an emitter follower, an emitter follower. See, 2500 by 100 is 25, right? So 25 parallel with anything should be less than 25. 25 ohms parallel with it, 24.67. Some are saying 24.92, 24.67, 20. Maximum are saying 24.67. So I'll go with 24.67. It should be less than 25 ohms, right? 25 parallel with 8K. So this is the common collector amplifier, right? Sandeep is giving me a very special answer, right? Sandeep is telling me 24.6767258482418828. Very good. Very good, Sandeep. You made my day, right? With all the decimals. Okay, good. So what is the last configuration we are left with now? What is the last configuration we are left with? The last configuration we are left with is common base amplifier. It is common base amplifier. Am I right? So let's change the page now. for the common base amplifier, calculate the AC parameters. Please, the same thing, right? The same question. I'm repeating it here. Beta 100, VD 25 millivolt, VA. What is VA? VA is infinite. Beta is 100. VB on 0.7. VT is 25 millivolt. Right? Okay. So in a common base amplifier, which terminal is grounded? In common base, who is grounded? The base terminal is grounded. Input is given at. Now, in a common base amplifier, let us directly go for AC analysis, because the DC operating current I'm giving it, right? I'm directly giving so that we can save some time, right? So now tell me, where is input given? Input is given at emitter. Input is given at emitter. Output is taken at collector, and the base is grounded. So you can calculate R in seen through emitter and R naught here. And this is your V naught. Input is given at emitter, output at collector, the base terminal is grounded. It is a common base amplifier. Input is given at emitter, output is taken at collector, the base is grounded, right? So let's start first DC analysis. DC we have already done because the DC current is given, but okay, we'll write the steps, right? Capacitors are replaced with open circuit. Vin is replaced with short circuit, right? Only DC sources should be there, right? DC sources. So what is IE? IE is again 1 milliampere. IE is 1 milliampere. Then what is IC? It is 0.99 milli. What is R pi? Beta by GM. 100 by GM is IC by VT. So this is 2.5K approximately. And your small signal model is the same. Oh, I would have changed the current, right? For all these problems, it's 1 milliampere. Okay. 2.5K. Here you can have GMVB. This is VB. Or beta IB, your wish. The previous problem, it is beta IB. Now, again, we come to GMVB, right? You can make it beta IB also. So this is the small signal model. And what is GM? GM is IC by VT. GM is IC by VT. Okay. So now draw the AC equivalent for it. Draw the AC equivalent. DC sources are shorted to ground. Capacitors are replaced with short circuit. And all of you, what should I do to current sources? If VCC is replaced with short circuit, current sources are replaced with what circuits? Open circuits, right? Current sources. Current sources offer large impedance. Voltage sources offer less impedance. Is it not? What is a low voltage source? An amplifier is a voltage source if its output resistance is 0. An amplifier is a current source if its output resistance is infinite. So if you have a current source, its output resistance is very high, so you can treat it as an open circuit. And here we have a 10K. The other end of 10K is shorted to ground. So you have BJT here, R pi, GMVB, and base terminal, emitter, collector. So base is grounded. Collector to ground there is 10K. And the output is taken at collector with respect to ground. Okay. So now, once we have done with that, we will start the shortcuts, right? The shortcuts means what? Don't do anything. Just tell the answer, right? You don't have to do all this. You don't have to remember any of the formulas, right? Because we are going to do it directly. By seeing the circuit, we can tell the answer. There is no need. It's not by remembrance, please. It's not that you remember something and tell. Don't, right? Because in the class, I'm going to do at least 20 varieties of common emitter, 20 varieties of common base, 20 varieties of common collector with different resistors here and there. But we are not going to do any of this. The moment a circuit is there, just write the answer. Are you getting? By logic. That logic we have to develop. It's not by remembering the formula. If you remember this formula, what happens if I just put a voltage divider at the input, or connect 1 or 2 resistors here and there, or connect 2-3 transistors in combination, then all the answers that you remembered are waste. Are you getting? We are not going to remember anything. We are going to apply a logic of arriving at all this, right? Okay. So that's more fun, right? Not doing this textbook way of doing it is okay. First time I will do it, but after that we will see how to avoid it. Are you getting? First time you have to do all this. So why? How is 8 5s are 40, right? 8 5s are 40. First you have to do it once, at least you have to do it. You have to add 8, right? 5 times, right? 8 1s are 8, right? 8 plus 8 plus 8, something like that. And slowly, first 1 BJT you do it. Then you combine 2-3 BJTs. You directly see and arrive at the solution, right? We'll do that first time when you're doing. We'll do it slowly. See, you will. That's when you appreciate the shortcut. To appreciate the shortcut, you have to do the textbook, the long way of doing it. And finally, when we arrive at the shortcut, we realize that these things are much, much simpler, because the effort that we are putting for a single circuit, 10 times, 100 times less effort we will put for 5 transistors, 10 transistors in combination, right? We'll do that. Okay. Now tell me, if this is GMVB, what is the current in the opposite? This is GMVB. The current in the opposite is going to be minus GMVB, right? So what is V0? V0 is minus GMVB into the collector resistor RC. And what is Vin? Give me a Vin in this loop, KVL. VB plus Vin equal to 0. Or your Vin is minus VB. Now what is V0 by Vin? Equation 1 by 2 gives you voltage gain. What is voltage gain, AV? V0 by Vn. So V0 by Vn, if you do it, you're going to get VB cancel. It is plus GM into RC. All of you, I told you what is the gain of a common emitter? The gain of common emitter is minus GM into RC. But the gain of common base is plus GM into RC. So please keep this in mind, that common emitter gain and common base gain both are same, except for that sign change, right? The voltage gain of common emitter minus GM into RC, the voltage gain of common base is plus GM into RC, right? Okay, so what is the input resistance I in here? I in. So there's some current that is flowing here. There's GMVB. So what is the total current here? The total current is going to be, what is the total current here? It is IN equal to minus of the total current. What is the total current in the opposite? It is VB by R pi plus GMVB. VB by R pi plus GMVB. And what is Vin? Vin is going to be minus VB. Minus VB. So defining input resistance. Input resistance Rin equal to Vin by I. Minus gets cancelled. VB also gets cancelled. It is 1 by GM plus 1 by R pi. Right? It is 1 by GM, 1 by R pi plus GM, or rather it is R pi parallel with 1 by GM. It is R pi parallel with 1 by GM. It is the input resistance. So if you do this, this comes to alpha by GM. So just do the parallel combination. R pi into 1 by GM by R pi plus 1 by GM. So that is alpha by GM. A common base amplifier input resistance is going to be, see here, the base, what is the resistance seen through base terminal here? Base terminal. It is R pi. But if you see through emitter, it is R pi by 1 plus beta. which is approximately alpha by GM, right? Or it is R pi parallel with 1 by GM, whatever. So you just calculate the values, you will realize this. So when I give you a shortcut, I will explain this once again, right? So here it is R pi, but here it is R pi by 1 plus beta, which is alpha by GM. You divide that by 1 plus beta times. Input resistance. Then what is the current gain? What is the current gain now? The load current here, IL, is going to be minus GMVB. Okay, so let me change the page here. Or I'll write it here. IL is going to be minus GMVB. Right, IL is going to be minus GMVB. And what is IN? IN is going to be, what is IN? IN is going to be VB by R pi plus GMVB. So the current gain is defined as current gain is denoted by AI. It is IL by IN. It is IL by IN. So what is IL by IN going to be? Here it is minus GMVB, and IN in terms of VB is this VB by R pi plus GMVB. So IL by IN is going to be GM by GM plus 1 by R pi. So what is R pi? R pi is again beta by GM. So tell me, what is the current gain value? What is the current gain value? 1 by R pi. R pi is around 2.5K. 1 by 2.5, 0.000, something like that. And this GM is there. Now, can I say GM R pi is much greater than 1? It is GM R pi by 1 plus GM R pi. If my GM R pi is far greater than 1, then this value is almost going to be 0.99. So current gain, common base, is also called a current follower, or a current buffer. Common base is also called a current follower or current buffer, right? CB. Input resistance. What is the output resistance of the amplifier? Output resistance. R naught. Output resistance R naught. So you're applying V in here. V in is also connected to ground. And you have an RC here. And if you're finding here, your R naught will also be equal to RC. Am I right? Your output resistance is RC. So if you want, you can draw the small signal model. And here the voltage is shorted. Here, somewhere here you have a voltage source, your IB is 0. GMVB, it is also 0. You have RC. And here you can connect 1 volt source. 1 volt, find current. The whole current will flow here, right? 1 volt equal to IX into RC. R naught equal to 1 by IX, which is RC. But if you take here, your output resistance is going to be infinite. If you take, right, if you treat RC as the load and remove RC and calculate, then your R naught is going to be infinite. So these are the 3 configurations with the small signal model. But how to avoid all this? how to avoid all this and have a shortcut. Have a shortcut where even if there are multiple transistors, we can just, by looking at this circuit, we can come to a conclusion, right? Yeah, plus please give me the values, no? I forgot. What is GM value? 0.99 milli by 25 milli into 8K. There's a value. Input resistance is alpha by GM. Alpha is almost 0.99. 0.99 by 25, around 25 ohms, right? Approximately 24.7 ohms, something we got. So the output resistance of common collector is the input resistance of common base. Can you see? Common collector output is at emitter, common base input is here. So both values are same, 24.7. We got alpha by GM. So let me summarize here. Common base amplifier. Low input resistance. Low input resistance. So amplifier is current control. Current control. See, if I directly tell you a shortcut, what is the validity of such a shortcut, you tell me? In the comment section, so many people are writing, sir, do we have to do all this? You just tell shortcut. If I tell you a shortcut, how will you, what is the validity of it? Now we know the values. Through shortcut, I'm going to prove for 1 transistor, 5 transistor, 10 transistor, then we will be having, a ground where we can compare things, right? And I even want the summary of the 3 configurations. To get the summary, at least 3 problems we have to do by the normal method. Are you getting? So you should have patience. This is the last problem we are doing by the small signal. And now we can see what is the quick way of arriving things, right? Low input resistance, high output resistance. So if you treat RC as load, then you will have infinite resistance, I told you. High output resistance, the amplifier is current source. Current source. So common base amplifier is a current controlled current source. Current controlled current source. And the current gain is approximately 1. So it is also called a current buffer. Current buffer. And it has high voltage gain equal to the common emitter. The high voltage gain, this is equal to the high gain of C amplifier, right? Equal to the high gain of C amplifier. Now, what is the power gain AP? It is AV into AI. It is approximately AV. Now, is there any negative sign in the final answer? Maybe a couple of negative signs here and there, but final answer, everything got cancelled, right? So everything got cancelled, and the final answer, you are free from any negative number, right? So no phase shift of both voltage and current. Both voltage and current. So you can just compare this, just for comparison, you can have the CC amplifier we have done just in the previous case. Here you have low input resistance. Here you are going to have high input resistance. Can you see? If you remember one, the other you can easily know because they are completely complementary to each other. High Rn, low R0. Here AI is 1, here AV is 1. Here you have high AV, here you have high AI. And the power gain is approximately equal to current gain. Here the power gain is the voltage gain. So completely complementary, the common base amplifier and the common collector amplifier if you compare them. Okay, so students are writing in the comment section, sir, please inform when is tomorrow's class. Tomorrow's class. So many people, right? Tomorrow's class will have same time. We will have same time between 5 to 9. Okay, so tomorrow's class same time we are going to have. Okay, so what about the summary here? The summary, have you checked the summary here? The common base summary and the common collector summary. If you remember one, then you know the other, right? So if you remember one, then you very easily know the other, right? And Sunday also we will have 2 sessions only, right? Any day I'll take 2 sessions. We will not have long session on Sunday, like from 2 o'clock like that. If it is even from 2 o'clock, then we'll take from 2 to 4 one slot, and we'll have a break, and then 6:15, 6:30. 2 to 6:30 we'll take on Sunday. Is that okay? Right? Everybody, 2 sessions is okay, or you want 3 sessions on Sunday? Harsha is saying okay. 2 sessions okay, or 3 sessions you want on Sunday? 2 sessions. Okay. Fine. We'll have 2 sessions on Sunday also. Okay. Now, what is the shortcut? What is the intuitive way of solving this? This, I'm going to call this as the resistance reflection rule, right? So I'm calling this as what rule? Resistance reflection rule. If you ask me what is a resistance reflection rule, I'm going to convert transistors into resistors. For example, if 2 transistors are in series, like how easily we will do the 2 resistors in series, right? R1 plus R2, the same effort we are going to put even for a transistor. Even for a transistor, if 2 transistors are in series, the same effort that we have for 2 resistors, R1 plus R2, only the same effort we are going to put, right? So how do we do that? The first rule 1 is rule 1. See, BJT has 3 terminals. If you check what happens at 3 terminals, so that's it, right? The first rule says that if you're looking at the base terminal Rin, the resistance we know it is R pi. The resistance we know it is R pi. If you apply a voltage V and inject a current I, your V by I is going to be R pi, right? How is this? That means anytime, suppose this is node A or node X here, anytime I'm applying a voltage source to X, what I do is I will simply remove that transistor, and from the node X to ground, I'm going to connect an R pi resistor. So this is my first rule. My first rule says that anytime I find, so the moment there are 10 transistors, remove 1 transistor, put a resistor, remove 1 transistor, put a resistor, remove a transistor, put a resistor. Then the combination of 3 transistors will become 3 resistors for you. So it's much easier for you to solve, right? So if you apply a voltage source V and find current I, your V by I is R pi, the same thing is expected from this transistor circuit. So that means this transistor circuit is equivalent to this resistance. Okay, then what is the proof for this? The proof we have seen in the common emitter. Once again, let me draw the small signal model here, R pi. This is the node X, ground. And here you are applying a voltage V, I. So this I is IB. Am I right? So what is V by I? V equal to I into R. V equal to I into R. Or V by I is R. V by I is what? R. So anytime you find a BJT, just remove that BJT. And where you have to connect that resistor, please connect the resistor where you have connected the source. From that point to ground, you have to connect it. Now you tell me, Please do Ohm's law for this network. This is the BJT. Ohm's law for this network. V by I is R pi. Right? Now, the rule 2. Rule 2 says that if I'm seeing through the emitter, if my X node is here and I'm seeing through the emitter, then what is my input resistance? My input resistance is not R pi. Is not R pi. Through base it is R pi. Through emitter, the current here I has increased. What is the difference between this current I and this current I? What is the difference between this current I here, this current I and this current I? This current I in the second diagram is 1 plus beta times more than the resistance of the first diagram. And please, resistance R is always equal to resistance is voltage by current. Voltage by current. Should never forget Ohm's law. Resistance is voltage by current. If current increases in the denominator, then the resistance is going to decrease. If the current increases in the denominator, then the resistance is going to decrease. So this resistance, because the increase of current is going to divide by 1 plus beta. It's going to be R pi by 1 plus beta. So what is your Rin? Your Rin is going to be R pi by 1 plus beta, or it is alpha by Gm. I think it's better we write alpha by Gm. The reason is when you go for MOSFET, alpha is 1. When you go for MOSFET, if you cultivate this habit here, alpha by Gm, the moment you shift to MOSFET, alpha is 1, your beta is infinite. All the answers that are there for BJT will simply convert to MOSFET. You just simply convert to MOSFET, and you feel that you have finished two of them, right? Both BJT and MOSFET just by a single effort, So what is your Rin? This BJT is equivalent to, this is a node X here, and you have to connect a resistor. Its value is alpha by Gm. Its value is what? Alpha by Gm, or R pi by 1 plus beta. Why did I divide it by 1 plus beta? Because if the current increases by 1 plus beta times, your resistance is also going to get divided by 1 plus beta times, right? So this is rule 2. Rule 1, please, rule 1, what is the resistance seen through base? R pi. What is the resistance seen through emitter? R pi by 1 plus beta, or it is alpha by Gm. This is rule 2. Now the rule 3, okay, what is the proof for rule 2? The first rule, second rule. What is the proof for the second rule? If you want a proof, here I'm connecting a voltage V, and this is I. Here you have R pi, and here this is beta IB or GMVB, right? Then if you have IB here, then what is this current? It is 1 plus beta times of IB, is I. So your I is minus of 1 plus beta times of IB, and your V is going to be, if you apply KVL here, minus IB into R pi. So your V by I is going to be R pi by 1 plus beta alpha by Gm, right? R pi is beta by beta plus 1. It is going to be beta by beta plus 1. R pi is beta by beta plus beta by Gm by beta plus 1. It's alpha by Gm. We can take alpha by Gm. Okay, so this is rule 2. Simple. Rule 1, the resistance seen through base is R pi. The resistance seen through emitter is alpha by Gm, right? Now, what happens if rule 3 is, what happens if I connect a resistor from emitter to ground here, R or RE? Tell me, what is the resistance seen through base here? You have R pi, am I right? But when you inject a current I or I in or IB here, this current gets multiplied by 1 plus beta times. So it is going to be R pi plus 1 plus beta times of RE. Now you might say, no, how did I multiply by 1 plus beta? because here you're injecting a base current, but the actual current is the emitter current. It is how many times? 1 plus beta times of that. So you have to multiply by 1 plus beta. So you can remove the whole circuit and you can put a resistor here whose value is R pi plus 1 plus beta times of Re. See, if you do this, it's so much fun. Why? Because now you can have multiple transistors. You have to keep on multiplying R pi plus 1 plus beta times of Re. Are you getting? You keep on multiplying any number of transistors. You go from base to emitter. You always have R pi plus 1 plus beta times of Re. So if you want, I can just give you an example. See, if I give you an example here, what if I have a transistor circuit like this, right? Like this. And you're asked to find the input resistance here. R1 and R2 and R3 like this. There's so many, right? But if you do by small signal model, it just blows your mind. Instead, what we can do is, whenever a network is given like this, and you're asked to find the input resistance, what will you do? If you're asked to find input resistance here, suppose this is 1 ohm, 2 ohms, 3 ohms, 5 ohms, and 6 ohms like this. Whenever you're calculating input resistance, you should always start from here. Can you, right? Should always start from here and then go towards this. 1 plus 1 is in series. Then the combination is in parallel. 2 parallel 2 is 1. 2 plus 3 is 4. 4 parallel 5 like that. So similarly, while solving this, what is the resistance of this circuit? The resistance, you can replace the whole transistor here, the whole box here, and you can put R pi here. Because the rule 1 says that, you can remove a transistor and put a resistor. We'll do this a lot of exercises, but I'm just telling you. Then this R pi and R3 will come in series, right? And then you have to see here, what is the resistance of this? Now I have to replace this whole thing by a resistor. What will I do? R pi plus 1 plus beta times of this R3 and R pi are in series. Are you getting? So we'll do this. It's more fun, right? We'll do this. Like that, you can keep on piling up any number of transistors, right? So you have suppose you have 2 transistors like this. 2 transistors. So what is the resistance of this guy? R pi. Then you can do like this. Here you can connect R pi. Then now what is the resistance here? It is R pi plus, you go from base to emitter, you have to multiply by how many times? 1 plus beta, right? Okay, so we'll do this. Because we are running short of time. No problem, right? So this is rule 3. The last rule, the rule 4 is, you know what is rule 4? The rule 4 says that if you see through emitter, the resistance is alpha by Gm. What if you put a resistor here, R? Now you're going from emitter to base. If you go from base to emitter, you're multiplied by 1 plus beta. If you go from emitter to base, what is your input resistance? It is alpha by Gm plus this resistance, the current is small, base current, but we are injecting an emitter current. So it is going to be R divided by 1 plus beta. So the rule 3 and rule 4, please see rule 3 and rule 4. If there is a resistor at emitter, you are seeing through base terminal. It is R pi plus 1 plus beta times of Re. If there is a resistance at base, you're seeing through emitter, you have to divide that resistance by 1 plus beta times, right? So now you can solve so many circuit, differential amplifiers and all that you're seeing through emitter terminal, you can very easily solve because you're just replacing the transistor with a resistor, right? So what is the proof for this? If you want to prove for this, yeah, here we have a beta IB, this is R pi, and here there is Re. Now the total current is 1 plus beta times of IB. This is V. This we have seen in common collector, right? Here you have IB. So now you tell me what is V? The voltage V here. The voltage V here is going to be IB into R pi plus 1 plus beta times of IB into Re. So your V by I is going to be this. Your V by I is going to be this, right? R pi plus 1 plus beta times of Re. So this is very, very important. So only 4 rules. I repeat 4 rules. What are the 4 rules? C through base terminal, R pi. Second rule, C through emitter terminal, alpha by Gm. Third rule, if you go from base to emitter, that resistor should be multiplied by 1 plus beta. If you go from emitter to base, those resistors you should divide it by 1 plus beta. So if you know these 4 rules, now you can challenge, right? You can say, give me 5 transistor, 10 transistor, but we'll go slow. We'll go slow. I'm not going to do with such a big problem initially. Just 1 transistor, 1 resistor. Then we'll put an extra resistor. Then we'll put a resistor at base. Like that, if you combine them, then things will be much clearer, right? We can't do big problems like this. So we'll go slowly, slowly. 1 resistor, 1 resistor will keep on increasing such that we finally get a clear idea on this, right? So any difficulty in the rules? Not much, right? Base terminal, R pi, emitter terminal, alpha by Gm. Go from base to emitter, multiply by 1 plus beta. To go from emitter to base, you have to divide by 1 plus beta. Okay, fine. So we'll stop now. We'll have some questions, right? Venkat, unmute the students, please. Okay, any doubts? Venkat, unmute.
Hello, sir.
Hello. Yes.
Good evening, sir.
Evening.
Sir, we have analyzed the CE now, sir, by small signal model.
Yes, yes.
We have found that the voltage gain and current gain is very high now, sir, for CE.
Yes, yes.
Sir, if we cascade them, then the linearity property would be lost, no, sir.
No.
Because the input signal of second transistor would be
Yeah.
signal, no, sir.
Yes.
I'm always confused with that, sir.
Okay. That's a good doubt actually. When you are cascading stages, the overall gain we have to see. The overall gain from where the first transistor to the last transistor, from the input to the output. If you see and calculate the gain, your gain will be very large. But there might be some distortion because the next stage, if you are combining them, they have to encounter a large signal. Yes or no?
Yes, sir. Yes, sir.
So in such an occasion, to improve linearity property,
Yes.
you can always have some sort of feedback mechanism.
Okay, so.
Yeah, if you give negative feedback, then definitely the linearity is going to get improved.
So the total output which we are going to get in first amplifier is going back to the same, sir.
Yes.
So we are getting a lesser input.
The point is, in olden days we had amplifiers which are like a train. They are connecting first stage to second stage, third stage. That drama is not there in the present day. In the present day, a single stage amplifier will give you a large gain. How? The maximum gain you can expect in an amplifier is GM into R0, where R0 is what you call early voltage by ICDC, that's in mega ohm.
Yes,
So a two-stage amplifier itself in a op amp is going to give you gain in lakhs. But in old books, how you get because the load is passive load, no? The resistors. But in the present day world, load is active load. Active load means your RC is not RC, it is another transistor.
Okay. Like what you have explained now, sir. RPi.
Yeah, the RPi is okay. RC resistor is there, no? Physical resistor.
Yes, sir. Yes, sir.
Instead of that physical resistor, this is next tomorrow's class. In tomorrow's class, what we are going to do is, suppose I'm having a common emitter like this. This is a common emitter, right?
Yes, sir.
I will have a load like this, I'm saying.
Okay. Okay.
Now, this R0 is going to be the gain. The voltage gain is minus GM into R0. This R0 is in mega ohms. So the gain is going to shoot up 10,000, 50,000 like that.
Yes, sir.
Are you getting?
Yes, sir. Yes, sir.
So in such an occasion, you don't have to worry about what? You don't have to worry about the cascading.
Okay, sir.
Because the load is no longer passive load, it is going to be active load. So we will come to that. Today we have done, we've been a little bookish and we have been a little boring today, right? Take the DC analysis, then AC analysis. We have done that. From tomorrow's class, what we are going to do is, we are going to solve them intuitively, because the moment a question is there, just analyze, write the answer. There are no two steps. But first we have to do what is there in the book, no?
Yes, sir. Yes, sir.
Without doing the book, you cannot summarize it. And after that, from tomorrow, we can have a flavor to this discussion. Okay?
Sir, and again in MOSFET also we would have that current gain is infinite, no, sir?
Yeah.
Then there also the same feedback mechanism is going to apply, sir, or what?
No. What I'm saying is, suppose you have a passive load,
Yes.
and you are having a series of amplifiers connected in cascade, and you
Yes.
have a problem with the linearity, then you can go for negative feedback, I'm saying.
Okay.
But a MOSFET and BJT, single stage itself will give you gain if you have an active load, I'm saying.
Oh, yes, sir.
So these amplifiers should still deal with small signals, but their output is very big signal, single stage itself.
Yes, sir.
Are you getting?
Yes, sir. Got it, sir.
Yeah. If you have passive amplifiers with passive load, then to improve linearity, you can always give negative feedback. Okay.
Good evening, sir.
Hello.
Yeah,
Sir,
good
and again,
Hello.
sir, I'm unable to differentiate between common emitter and common collector, sir.
Common collector, your output is taken at emitter, no?
Emitter is grounded, collector is grounded, that point, sir.
Emitter is grounded.
In common emitter is grounded, no, sir. Common collector,
Collector is grounded, no? In
Sir,
common collector is connected to VCC. This is ground for AC analysis. Input is here, output is here. This is common collector.
Okay, sir.
Common emitter is grounded, input is given here, output is taken at collector. This is common emitter.
Sir, in common emitter, the collector part, if you keep the resistance, you said that there is common collector only, no, sir?
Where you want to keep? Acha, here you want to keep. If you want to keep, you can keep, but put a bypass capacitor here.
Okay, sir.
Because the capacitor will act like what? Short for AC analysis.
Yeah.
Then the collector is again connected to ground.
Yes, sir.
Yeah.
Sir, and again, VA is infinite, you said, no, sir. That is what condition, sir? I did not.
Early voltage. R0 is early voltage by IC/DC. You see the fluctuations between VC and IC. If this is infinite by anything is infinite, no? Your R0 is infinite. So we have not included R0. Tomorrow we are going to include R0.
Yes, sir.
Are you getting?
Yes, sir. Yes, sir. Got it, sir.
Hello.
Yes.
Yeah, good evening, sir. When you are cascading, no, sir, two transistors.
We have not cascaded, no, till now. Don't worry.
When will R0 come into action, sir? Then?
No, even for a single transistor, R0 is going to come into action tomorrow.
Okay, sir. Can you show the slide of first problem emitter, common emitter?
Common emitter, number?
Number I don't remember. First problem.
This one only, no?
Yeah, small signal analysis.
Yeah.
Small signals.
This is a small signal analysis.
Yeah, this before one.
Acha, this one. Tell me.
Yeah, that's it. I want a screenshot. I missed the class. I
Okay.
missed it. Yeah,
Hello.
thank you.
Good
This is the
evening.
first
Hello.
one you want screenshot for this?
Hello, sir.
Sir.
Hello.
Yeah, tell me.
Sir, 12F, sir, transconductance, I'm not able to understand. For early effects, sir, second number in small signal model of BJT.
Yeah.
Yes, sir. Sir,
I'm defining the fluctuation of IC with VB as transconductance.
yes, sir.
What do you mean by transconductance? The term conductance means it is the ratio between the current and the voltage.
Yes, sir.
So I see, instead of saying that ICVB, 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 we are using the word GM.
Yes, sir.
GM is going to relate the output current with the input voltage. It's the ratio between the output current and the input voltage.
Okay.
So this term GM is telling you how IC is going to fluctuate with VB.
Okay.
How IC is going to fluctuate with IB, beta is going to tell. Beta, the word beta tells how IC will fluctuate with IB.
Yes, sir.
Transconductance tells that how IC is going to fluctuate with VB.
VB.
This is a
Sir.
definition.
Sir, how is then is equal to ICDC upon VT, sir?
Very good. This GM, already we have done this calculation, small signal analysis of diode.
Oh, yeah.
So slope, instead of applying a small signal, there I told you that the slope means change in IC by change in IE. So
Yes.
slope in mathematics is differentiation.
Yes, sir.
Whenever you want to find slope in mathematics, what we have to do? That
Different.
function you have to differentiate at the operating point.
Yes, sir.
So I'm having that function. IC is IS into e power VB by VT is a function where IC varies with VB. Can you see this function here?
Yes, sir.
But on this function, I want a slope at this point. So I first differentiated DIC by DVB. I got some value. Now in this value, my slope is calculated not here or here or here, but here where the voltage is 700 millivolt plus the signal.
Okay.
So this is the total voltage, which is 700 millivolt plus the V in small signal. So the small signal is 1 millivolt, no?
Yes, sir.
So 700 millivolt plus 1 millivolt is 700. I put DC here. So this IS into e power DC value of VB by VT is ICDC.
Yes,
So
sir.
the operating point is going to decide the slope.
Okay.
This here, this
Oh.
slope is this point divided by 25 millivolt. What is the slope here? The point divided by 25 millivolt. What is the slope here? Point divided by 25 millivolt. So the slope is nothing but the operating point divided by the 25 millivolt. Are you getting?
Okay, sir.
Yeah.
Hello, sir.
Evening.
Yes.
Sir, you said that common base, common collector, common emitter is applicable only in small signal analysis, no, sir?
The term, whenever somebody is saying common emitter, it means they are all signal analysis, not DC analysis. DC only biasing.
Sir, in DC also we made that emitter is as grounded and we applied input to base.
There is
and
no
we take
input. Only 5 volt, 6 volt DC we have applied.
Means only biasing we did, but no signal, no
Only biasing, only static analysis we have done. I have never used the word fluctuation, and I have never put a small letter here. They're all only capital letters.
Okay, sir. Sir, another doubt, sir. Sir, this you told that this transconductance GM is equal to IC by VB, you know, sir.
Small
Means you
IC
said-
by small
you
VB.
said-
Its
means you-
value is IC DC by VT.
Means you said that these fluctuations are replaced by the resistor, no, sir.
Yeah, you get this
can model.
fluctuation I have replaced by a current source, dependent source. R pi I have replaced by resistor. This GM fluctuation is this current source. Can you see here?
Oh, yes, sir.
This is going to tell me the fluctuation between IC and VB. This is going to tell me the fluctuation between VB and IB. This is going to tell me the fluctuation between VC and IC.
Sir,
Finally,
sir, Sir, VB is temperature dependent now, sir, but RPI is a passive element now, sir.
Yeah, this is just a model. V by I is replaced by R. That's all. It's a model.
Okay, sir.
Are you getting? See, a bulb is there, sir. What did we do to the bulb? We replaced the bulb with a resistor. Do you remember?
Yes, sir. First
You
class.
think a bulb is a resistor? Resistor means in market we will find bulb is its character is that resistor. So the BJT character, the fluctuation of VB and IB, this R5 will tell.
Means just for analyzing the circuits,
This is an
just we did
equivalent
it.
circuit, an
Yes, sir.
equivalent circuit of the BJT. Its characteristic when you apply a small signal. So when
Yes,
you
sir.
apply a small signal, how the BJT voltages and currents are fluctuating, this model is going to tell you.
Okay, sir. Got it.
Are you getting?
Yes, sir. Got it, sir.
Yeah, good.
Hello, sir.
Sir.
Yes.
Sir, why we took sir same page, sir?
Yeah.
Why we got minus GM, sir? Why minus IC?
No. The short circuit. See, model means it should be a Thevenin model or Norton model, no?
Yes, sir.
The first Norton model I'm drawing. If you want, you can replace this by source transformation. Thevenin model you will get.
Okay, sir. Okay, sir.
If you want Thevenin model, how it will be? The same R pi. This is minus GMVB into R0 in series with R0 you can have. Then that will become a Thevenin model. I have drawn the Norton model for it. What is Norton model? A current source in parallel with resistance, no?
Sir, sir.
But BJT current, can you see? It is in the opposite. See, this one is a block. This one is a box. Can you see? For this box, I have to find the output resistance and the short circuited current. Do you know what is a Norton equivalent? Are you getting?
Yes, sir. Yes, sir. Getting,
Yeah.
sir.
Hello, sir.
Yes.
Can you go to 9F, sir? 9F, sir.
9F.
Yes, sir.
Yeah.
Sir, here V naught less than 1, sir.
Yes.
Sir, how VDS 1 less than 1, sir?
How?
VDS 1 less than 1.
V naught is nothing but VDS. V naught is V naught with respect to ground. This is V naught.
Okay, sir.
And this is nothing but VDS1.
Okay, sir. Sir, another dot, sir. 14F.
Huh?
14F, sir.
Yeah.
Sir, you said one small signal analysis of BJT for early effect. Fourth, yes, sir. Sir, here R not equal to delta VC by delta EC, na, sir.
Yes.
Sir, how we can call that VCE, sir? If all capitals means DC, small means AC.
See, this delta VC means the total instantaneous value you are differentiating. dy by dx is this. All these are whenever we write small letters, it is dy by slope only, no?
Yes, sir.
Change means dy. In mathematics, they write dy by dx.
Yes,
Here we are writing small y by small x.
sir.
Are you getting? dy by dx is nothing but small y by small x.
Sir, I'm asking why you have written capital V, sir, for VCE.
This is instantaneous. Big capital, small. These two are small.
Overall output, na, sir.
Overall total instantaneous equation is there, no, for VC. And the
Ah.
characteristics.
Yes, sir.
For that the characteristics is not drawn for DC or AC. It is for total values.
For the total, we are representing like this.
Total that you have to differentiate delta.
Sir, can we say transistor is a transfer of resistance?
Yes, of course, it is a transfer of resistance. Yes.
Sir, another doubt, sir. Sir, why we are grounding emitter base collector, sir? Why we have common configurations?
No, input can be given to only one terminal. Output can be given to another terminal. One of the terminals should be ground, no? That is why 3-terminal devices are so popular.
Okay,
Because
sir.
input port, we need one terminal, output we need. The third terminal, we will ground it to create a loop. Like that, you can give for in 3 ways because 3 terminals are there.
Okay, sir.
Are you
Thank
getting?
Yes, thank you, sir.
Hello, sir. Hello,
Hello,
sir.
sir. Rule
Yes.
4, sir. Rule 4.
Rule 4.
Yes, sir.
What is rule 4? If you see through emitter, it is alpha by GM. If you go from emitter to base, you have to divide by 1 plus beta. No? Yeah.
Sir, this R pi by 1 by means alpha by GM is R pi by 1 plus beta. No, it should be only R pi, no, sir. In
Only R pi if you see through base. Yes. If the current is IB, then it is R pi. V by I. V by IB is R pi. V by
Yes, sir,
I
means-
is R pi by 1 plus beta. This is R pi by 1 plus beta. This one.
Okay, okay. Sir, means if we connect a resistor, if a resistor is present at the base, and if we look through the emitter, then 1 by beta would come for both the resistors. Means like R pi is.
Yes. Very good. Excellent point you have made. Let me see what the student is trying to tell is, if he sees through base terminal, there is R pi. So he's saying that if there is R pi and R, what if I divide it by 1 plus beta? Because I'm seeing through emitter. He's absolutely right. R pi by 1 plus beta is nothing but alpha by GM, and R he has divided by 1 plus beta. So if you go through emitter, then you have to divide those resistors by 1 by beta. Very good.
Okay, sir. Okay, that was that. Okay, thank you.
Yeah.
Hello, sir.
Equivalent to a resistor, right? This is node X. This is node X. From X to ground, from here to ground, this is alpha by GM plus R divided by 1 plus beta, right? Or it is R pi plus R by 1 plus beta. Okay. Next.
Hello, sir.
Yeah.
4F pager.
What?
4F.
Yeah.
In this ID1 equal to 4 by 3 also.
How ID1 is 4 by 3?
Yes, sir.
See, the fourth equation, you multiply by 2.
Okay, sir.
2 ID1 plus 2 ID2 equal to 4 you will get. Are you getting? This is ID1 minus 2 ID2 is 0. Then you have to add these two. Then you will get 3 ID equal to 4. Then ID is 4 by 3.
Okay, sir.
Are you getting?
Yes, sir.
Yeah.
Thank you.
Hello,
Yeah.
sir. Hello.
Yes.
Yeah, I have a doubt in yesterday's. You said that early effect can be avoided using the cascade current source. So
Yeah.
I understood because of the transistor below we are fixing, IC will be fixed. So,
Yeah.
but we see that for the second transistor, VCE will change. So
Yes,
because
because
of that,
load is changing, no?
yeah.
To
So because
satisfy
of,
Kirchhoff's law, when
Uh-huh.
load is changing, the total voltage from up to down should be VCC.
yeah.
So,
So if,
your VC will change, but
yes,
your IC cannot change.
yeah, okay. So if VCE changes, won't VCB also be affected? Because of that, the additional voltage, where does it go?
No, that's what I'm trying to say. Even if VC changes, there is
Okay.
no scope of changing the current. The reason is across that 1K resistor, the lowest one, the voltage is still 1 volt fixed, no?
Yeah, yeah. So
According to
VCE
Ohm's
will not
law, I
change.
equal to V by R.
Yeah, I got that, sir.
So
So
then the upper part, see above Q1 transistor, Q2 is there, no?
yeah,
Q2 is also like the load for Q1.
okay.
Even if load changes, voltage, RC changes, load. See, forget about Q2 transistor. If you put a MOSFET there in the place of Q2, the MOSFET is also going to have that beautiful characteristic, parallel to x-axis.
Okay, thank
Are you getting what I'm saying?
Yeah, I
The
got
Q1
it.
transistor is fixed. Now you might say, sir, what should I do to Q2? You do anything to Q2, but that current is not going to change. So the Q2 transistor, though your VC is changing, your ICs are going to be parallel to x-axis.
No, I was confused about what the addition, where does the additional, like, so it will act like a load. So VCB will not change? If
Where VCB will change, but the change in VB is very, very small.
Okay.
It's become stiff. You are taming that BJT. You are saying BJT or IC, because if VB changes, IC should change, you know.
Yeah, okay.
So this VC is changing. The whole reflection is there at VCB. But if VB changes, your IC should change. It cannot change. This is stiff 1 milli. This fellow pakka 0.7 he will give. 0.701, 0.701. It does not change. But if you use a single BJT, this will change. This will change. This will change. And the resistor voltage here will not be stiff 1 volt. It keeps on changing here. Your current will also change.
Okay, sir. Okay.
Are you getting?
Yeah, got it.
See, the point is you cannot get an ideal device. Previously, the characteristic was like this, no? Now the characteristic will be a little reluctant. He cannot go so freely. He'll come down.
Okay.
So here it is like 1 mega ohm. Here it will be like 100 mega ohm. If you put 2 transistors down and third transistor if you put, you will have 1 giga ohm. Are you getting? As you keep on increasing the number of transistors, the upper transistor, the most upper transistor is going to have this beautiful characteristic.
Yeah, okay.
Are you getting?
Yeah. Got
Yeah,
it.
think about it.
Yeah, okay, thank you.
Right.
Good evening, sir.
Yes.
Sir, I'm having an old doubt in amplifiers in where we discussed about filters.
Okay.
Sir, I'm finding a difficulty in all-stop filter and band-pass filter when we are using the omega is equal to 0 and omega infinity, like shorting the capacitor and open circuiting inductor.
See, all-stop is not at all a filter. It is just given in ISRO exam.
Okay, sir.
And why that is not a filter, I'm telling you. For omega infinity, that is open switch, no, across the feedback, it is going to saturate. The op amp is going to saturate in that all-stop filter.
Okay, so then in case of, all-pass filter and
All-pass filter, at least there should be one complete resistor divider from output to input so that you get some gain. There should not be any capacitor. This side resistor, feedback also, only resistor should be there.
Okay, sir, got it. But I'm not able to differentiate how to decide between all-pass and band reject filter.
That's what I'm saying. Band reject will have capacitors here and there.
Okay.
They will keep on changing the impedances.
Yes, sir.
So a filter means what? It has to select some frequency, no?
Okay, sir. Yes, sir. Yes, sir.
So naturally, when it is selecting some frequency, it has to attenuate at some other frequency. But an all-pass filter has only resistors from input to output through resistor divider. Such resistor dividers you will not find in band pass.
Okay,
You will find one or two capacitors even in the feedback.
Yes, sir. Yes, sir. So we can say that there will be no storage elements in all-pass filter.
Yes. Only one. But the gain is one, no?
Yes, sir. Yes, sir.
Only one capacitor we have connected because you need phase shift. It is basically a delay filter, no? Phase shift filter.
90 degrees.
Yeah, it is going to give from 0 to minus 180.
Yeah, yes, sir. Yes, sir.
Yeah,
so,
if you change that capacity, you'll get from 0 to 180 also, plus 180 also.
Yes, sir.
Plus 180 I've given in the material.
Okay, sir. Sir, and in Holland current source, can we say that the extra op amp which we are using is just to simulate a negative equivalent resistance?
Yes, beautiful. So that whatever sourcing the current is sourcing at the input, same thing you have to sync at the output.
Okay, sir.
The net effect is going to get cancelled.
Okay, got it, sir. Thank
Yeah,
you.
yeah.
Hello, sir.
Yes.
13, sir, page number.
Page number 13. Yeah. Tell me.
Sir, while explaining this, my internet connection got lost, sir. Can you please explain briefly, like
Yeah.
small signal? What are the points when you
Yeah, in small signal model, in my first class already I told you, the DC analysis is not the analysis of amplifier. The amplifier analysis means signal analysis. Signal means when a signal is applied, your input, suppose you connect a microphone to the base terminal or to emitter terminal, the signal will fluctuate, no? When the signal fluctuates because of the signal, the currents and voltage also will fluctuate. So I am having 4 fluctuations here. One is these fluctuations we have to model using resistors and dependent sources. So what is the first fluctuation? The first fluctuation is between IC and IB. So wherever IC changes with IB, you simply call it as beta, I am saying. The second one is how IC fluctuates with VB. That I am defining as transconductance GM. And I calculated that fluctuation. I told you, whenever VB changes with IC, that is nothing but differentiation. So we differentiate, we found IC DC by VT. The third fluctuation is between VB and IB. VB and IB is a resistor because V by I is R, right? So VB by IB. IB I have written it IC by beta, beta by GM. So R pi is nothing but beta by GM. So finally we combine all the fluctuations into a model like this. So what this model tells, somebody asks you, what is this telling you? You have to tell that a real world BJT, an actual BJT, when you connect, this voltage will change, this current will change, this voltage will change, this current will change when you apply a signal. So who is changing with whom, we don't know. This model will tell you. This model tells that R pi is the change between VB and IB. GM is between IC and VB. R0 is going to be the output resistance. This is the Norton model. Do you know what is a Norton model?
Yes, sir.
In parallel with resistance. No?
With resistance.
Yeah. So for the transistor, I'm drawing the Norton model. I took a short circuited current and I calculated the output resistance. Then the short circuited current happens to be opposite of IC. Then I put a negative sign. Then I said, okay, I don't want negative sign. I want to remove the negative sign. So I changed the current direction here. Can you see?
Yes, sir. Yes, sir.
Yeah. So this explains the fluctuations of voltages and currents in a BJT when a signal is applied. That is why it is called the small signal model.
Okay, sir. This is current control current source, sir.
Which one? BJT. Yes. After biasing, you inject an IB, it becomes current controlled. But see,
Yes,
remember, don't worry about Thevenin, Norton, current, voltage. Why? Because any Norton equivalent you can convert to Thevenin, no?
Yes, sir. Yes, sir.
You do source transformation. What is there?
If I connect the R0 series, then it will be Thevenin.
You series and GM-VB into R0. GM-R0-VB will be the voltage.
Yes, sir.
But inherently, BJT after biasing is a current control current source. But don't think only Norton model should be there. Now, every Norton can be converted into Thevenin.
Thevenin. Yes, sir.
Yeah.
And sir, 28. Yes, sir.
Yeah. This one?
28. Yes, sir. Sir, here in diagram, in the left side diagram, sir, actually I'm getting confused. Like emitter is common between base and collector, so it is common emitter.
Emitter is common between base and
collector.
No, please remember, the model is not for a configuration. Amplifier will tell you the configuration. Model is for the BJT. So the same BJT model, you can use it.
Okay, for determining, we need to see the amplifier, sir.
Yeah. See, look at the amplifier. Oh, this guy got inside. How do I pull this line? Yeah. See here, when you look at the amplifier, you will know, not this model. See the amplifier here? Input is given at base, output is taken at emitter. Collector is connected to DC source. This will be replaced by ground, no? For AC analysis. This is ground for AC analysis. That means it is common collector only. Are you getting?
Yes, sir.
Input is at base, output
common
is at
collector, sir.
this is common collector. First one,
That means,
input is given at base, output is taken at collector, emitter is connected to ground through capacitor. Capacitor is short, no? What is capacitor?
Yes, sir.
Short for AC analysis. So who is short here?
Short.
Emitter is short. Common emitter.
Yes, sir. If voltage is given at emitter, then it is common collector. Sir.
You are right. If
Yes,
voltage
sir.
is given at emitter, it is common base, no? Common base. Here. Where is common base? CB. Yeah. Tell me here. See here. Input is given at emitter, output is taken at collector, base is grounded. Can you
Yes,
see?
sir. Base is grounded. Input is given at collector.
Emitter, output is taken at collector, base is grounded. So it is common base. Okay, let me draw like this. The same transistor, can I draw like this? Is it okay? Are you happy now?
Yes, sir.
Huh? Happy? Can you see
Yes,
base
sir.
is down?
Yes, sir. Yes, sir.
Yeah. Is it common base or not?
Yes, sir.
Ah.
Okay, that model we can light in any manner, but we need to see that
Yeah, a model is for the device, not for a configuration. You know what? In old books, for common emitter HIE, HRE, HFE, common base HIB, HRB, they have written pages and pages. Finally, they said that all are same. Are you getting? It is a headache.
yes.
If you use HIC for common collector, HIB for common base, if you use means finish. You can never solve problems.
Yes, sir.
Did I not get the same characteristics? Because a device, that is why new books, what they are saying, use the word pi. Don't use HIE, HIC. Student will get confused. Array, this is for common emitter. This is no. A model is equivalent of a device. Suppose op-amp is there.
Device.
RID, AVD, R0. That model you can use everywhere. Are you getting?
Yes, sir.
Yeah.
Yes, sir.
A model, remember, a
Sir,
model is for a device, not for the configuration.
Okay, okay, sir.
Okay.
Sir, last rules, sir.
Tomorrow again I will explain rules, sir. Before starting.
Hello.
Yes.
Hello, sir. Good evening.
Good evening.
సార్ ఈ బీటా అనేది మనకి ఇప్పుడు
చెప్పండి
ఈ బీటా అనేది మనకి మామూలు
హలో yes
sir, rules, can you please explain one second?
Yeah, I told you, base terminal, the resistance is R pi.
Yes, sir.
If you go from base to emitter, if you connect an emitter resistor, it is R pi plus 1 plus beta times of Re. R pi plus 1 plus beta times of Re. If you see through emitter, it is alpha by Gm. If you go from emitter to base, it is alpha by Gm plus R divided by 1 plus beta. These are the 4 rules I am saying. If you see through emitter, it is alpha by Gm. If you go from emitter to base, that resistance should be divided by 1 plus beta.
గుడ్ ఈవినింగ్ సార్.
Yes.
ఈ బీటా అనేది మనకి మామూలుగా ఐసీ వాల్యూస్ కదా సార్, ఐసీ బై ఐబీ, కానీ ఇక్కడ మనం ఏసీలో కూడా అంతే తీసుకున్నామని డౌట్ సార్, కొంచెం లైట్ గా.
అవును నాన్న, ఎందుకంటే ఏసీ అంటే ఏంటి? ఏసీ అంటే డిఫరెన్సియేషన్ అన్నమాట. యాక్చువల్ గా బీటా ఏసీలో స్మాల్ ఐసీ బై స్మాల్ ఐబి, దట్ ఈస్ డిఐసి బై డిఐబి ఇది ఏసీలో. కానీ డీసీలో ఏంటి? బీటా వచ్చి క్యాపిటల్ ఐసీ బై క్యాపిటల్ ఐబి కదా. సో ఇది ఎలా ఉంది ఈక్వేషన్? ఐసీ ఇస్ బీటా టైమ్స్ ఆఫ్ ఐబి. అంటే ఈ ఈక్వేషన్ y ఈక్వల్ టు mx లాగా ఉంది. కెన్ యు సీ?
సో dy dx ఆల్సో మనకి m.
dy by dx is also m. So it will be same beta value, no?
సార్ ఇక్కడ మనకి బీటా కరెంట్ గెయిన్ కాబట్టి సరిపోయింది సార్. కానీ మరి ఇప్పుడు ఒకవేళ మనకి వోల్టేజ్ గెయిన్ ఉందనుకోండి సార్, ఇప్పుడు ఆల్ఫా బీటా
లేదు, బీజేటీకి మనకి బీటానే ఇస్తాడు. అది లీనియర్ ఉంది కాబట్టి మనకి అడ్వాంటేజ్. నాన్ లీనియర్ ఉంటే అసలు అవ్వదు.
ఓకే సార్. సార్ ఇంకొకటి మనం ఇక్కడ ఐసీ వచ్చేసి మనం ఇక్కడ ఇంకొకటి జిఎం సెకండ్ దాంట్లో ట్రాన్స్ కండక్టెన్స్ వచ్చేసి క్యాపిటల్ ఐసీ బై వీటి రాస్తుంది. ఎందుకంటే అక్కడ మనకి
వాల్యూ వచ్చి క్యాపిటల్ ఐసీ బై వీటీ.
ఈ 0.7 అండి.
ఇప్పుడు అలా కాదండి, ఈ డివై బై డిఎక్స్ అనే వాల్యూ 10 అనుకోండి.
ఓకే సార్.
ఒకసారి డివై బై డిఎక్స్ రాస్తా అంటే చేంజ్ ఇన్ ఐసీ బై చేంజ్ ఇన్ విబి రాస్తా. దీని వాల్యూ 10 ఎక్కడి నుంచి వస్తుంది? ఐసీ బై విటి చేసినప్పుడు వస్తుంది. దాన్ని కట్టాలి కదా మనము, క్యాల్కులేటర్ పెట్టి కట్టాలా? క్యాల్కులేటర్ లో డిఐసి బై డివిబి కట్టలేం మనం. దానికి వాల్యూ కావాలి. ఆ వాల్యూ వచ్చి ఐసీ బై విటి.
ఓకే ఓకే. సో మనం ఏసీ అనాలిసిస్ వచ్చినా మనకి ఏసీ అయినా కానీ వాల్యూస్ అన్ని
ఇంపార్టెంట్. The DC analysis is dependent on the AC analysis is dependent on the DC operating point. The operating point is deciding the slope change.
ఇంకొకటి సార్, ఈ స్మాల్ విబిని మనం క్యాపిటల్ విబి అని రాస్తాం. ఎందుకంటే మనం ఆల్రెడీ 0.7 ఉంటుంది, 700 మిల్లీ వోల్ట్. మనం వోల్టేజ్ అప్లై చేసేది వీటి కంటే తక్కువ ఉంటుంది కాబట్టి
అప్రాక్సిమేట్ చేస్తున్నాం వాల్యూ. ఇప్పుడు వాల్యూ కట్టాలి కదా మనం. అక్కడ వెళ్ళి మీరు స్లోప్ కడుతున్నారు, కట్టినప్పుడు అక్కడ వాల్యూ ఆల్మోస్ట్ 700 మిల్లీ వోల్ట్ ప్లస్ సంథింగ్ ఉంది. సో మీరు 700 తీసుకొని దాని అప్రాక్సిమేట్ వాల్యూ ఐసీ బై విటి 25 మిల్లీ వోల్ట్ అంటున్నాం.
ఓకే ఓకే. సో మనకి మామూలు చేయట్లేదు కాబట్టి ఆ వాల్యూ అనేది దానికి ఈక్వల్ వస్తుంది కాబట్టి ఇది ఈక్వల్ టు ఐసీటీసీ బై విటి.
అంతే అంతే. డిఫరెన్షియేట్ చేసినప్పుడు వచ్చిన వాల్యూ ఇది.
ఓకే, thank you very much sir.
Right.
Hello sir.
Yes.
Good evening sir. Can you please go to page number 2F?
2F.
Yes sir. Second problem of today.
Yeah.
No sir, 1F. Second problem actually. Yes sir. Sir, here why M2 is off and M1 is on?
Why M2 is off? Out of these two, who experiences more potential difference?
Yes sir, M1. M1. Yes sir.
And M2, in that gate problem, he has given -15, minus VDD he has given. And here the source is -10. So what is -15 minus of -10?
Sir, but the 2 milliampere current source, will it have some voltage drop? I mean, BS is...
Of course, across this there will be a drop.
Yes sir. So how do we know that I mean it will be negative only, -15 minus of that voltage?
No.
At
We
VS
only know that this VS value is less than 3.
Okay.
This VS value is less than 3, such that there is a VGS greater than VT.
Okay. Yes.
Are you getting?
Yes sir.
Yeah, it
VT,
should be less than 3. That's it. That is what we want.
And VT value is also not. Is it given in the question, sir? I mean,
VT 1 volt, no, generally 1 volt, 0.5 volt will be there.
Okay. Thank you very much.
And let me add something to the discussion. Yes. 2 milliampere, if it flows as ID1, what is the drop across 1K? 2 volt, no?
2 volt, yes sir.
10 minus 2 is 8 volt is there at drain.
Yes sir.
8 volt at drain, any voltage less than 3 at VS. Your VDS is greater than VGS minus VT.
Yes sir. That's
it is in saturation, no?
Okay sir. And sir, another thing, if M2 is off, then I mean it is in cutoff, so we can actually
you can replace by open switch.
Okay. Fine.
You can just remove M2.
Okay. Thank you sir. Thank you very much.
Right. Okay, next. Anybody else?
Sir, completed, sir.
Completed, huh?
Yes, sir.
Okay, thank you.
Thank you, sir. Good night, sir.
Yeah, good night.